Much for being here during the first session of the meeting early in the morning. Many of us have just seen the sunrise for the first time. We really do appreciate you taking the time to join us today. This session is Early Mars Geomorphology. Resistance to erosion is futile. That is true on Earth because of weathering. Weathering is the right answer. And I'd like to introduce my co-chairs, Joel Davis from Imperial College London. Madison Turner from the University of Chicago is the moderator. I'm Ross Irwin from the Smithsonian Institution. We're starting with a 5-minute introduction to the session and just a few pointers for the speakers. There will be 4 oral sessions at 10 minutes each. There is no time for turnover between those presentations. And so as you're presenting, please watch the clock, which is down there on the floor in front of you, and make sure that your presentation stays to time. I hope that all of you will be able to meet that goal, but it's very important that we stay on time. And then after each block of 4 oral presentations, there will be a 20-minute Q&A. During the Q&A, please introduce yourself and your affiliation. Remote participants may submit the questions by Zoom Q&A. And also when you do that, please identify yourselves. No photography or streaming is allowed by the general audience. There are ambassadors who can post highlights unless the presenters explicitly say, please don't do that. But you have to do that proactively because the ambassadors are able to post highlights of the presentation unless they're denied that. For the speakers, because we have to turn over from one talk to the next very quickly, please make sure that you get mic'd up before the talk. There is on the remote control, there is a green button to advance the slides. There's a red button to reverse. Please don't use the laser pointer, or if you do use it, please don't rely on it because the folks who are joining us online won't be able to see it. The first speaker should take this opportunity to come and get mic'd up right now so that we're able to start here in just a few minutes. This talk, or this session rather, covers a wide range of topics, starting with a big picture history of water on Mars and going from that to glacial melting, the sedimentary clock, crater degradation, crater lakes, and then finishing off with local scale sedimentology at Gale and Jezero craters. Please remember to turn off your cell phones so that there won't be any interruptions during the presentation. And we will start here in less than 2 minutes.
Good morning, everyone. Our first speaker this morning is Bruce Jakosky, who's going to tell us about the history of water on Mars during the Amazonian and Hesperian.
Good morning, and thank you all for showing up so early on the first day after daylight savings time. I want to talk about the history of water. And to do that, you need to look at all of the different reservoirs for water, because water can exchange between them geographically from the mantle and the deep crust all the way up to the upper atmosphere and escape to space. But it can also exchange in ways that vary through time. For example, volcanic outgassing, which has occurred throughout history, has occurred at a declining rate through time. Loss to space, which also has occurred through history, also at a declining rate due to solar EUV and solar storms. If you go to higher obliquity, there's greater atmospheric water, greater exchange between the polar caps and the atmosphere. One consequence of that is, of having greater water, is you get more widespread ground ice. And because there's been so much loss to space through time, that means that earlier in history there was more water, which would result in larger polar caps. I'm going to go through each of these blue boxes and weave them all together. So first, if we look at loss to space through time, loss to space represents a balance between outgassing from the mantle and due to volcanism and escape to space. We can use D to H evolution as a constraint. I'm not going to go through the details, but we have a simple box model, one example of which is shown on the right, to look at how much water was initially present, how much has been outgassed, how much has escaped to space in order to look at the evolution of D to H. One consequence coming out of the models is that the average hydrogen and water escape rate to space over the last 3 billion years has been much greater than the present rate. You would end up with between 35 and 90 meters of water global equivalent layer and in the late Hesperian, and the amount lost to space constrained by D to H would be between 10 and 60 meters global equivalent layer. That compares to 2.2 meters at the present rate over the same time period. We can also use the history of the extreme ultraviolet, the EUV, to model the loss to space. The EUV flux as a function of time is shown on the left. It has declined by a factor of 10. In the middle, you can see the effect that EUV has on the extended oxygen corona that drives escape. More EUV, more corona, more escape. The models on the right come from Eric Chase-Fier. What we've done, rather than try to model each process, we've taken the simplifying assumption that every EUV photon that results in a photodissociation results in an escape when it's absorbed in the upper atmosphere. If you do that, you get loss of a little over 8 meters of water since the late Hesperian. And that may be a lower limit because that doesn't account for increased solar flares over that same time period. What this means is that loss to space since 3.3 billion years ago would be greater than about 8 meters of water global equivalent layer. This is consistent, broadly speaking, with the constraint derived from D to H. A consequence of this is that there would have been a lot more water in the near surface environment 3 billion years ago compared to today's amount of water. If we look at the effect of changing obliquity on the left, you can see the statistical variation of the chaotically varying obliquity. The red line is the current value. The obliquity was greater than present value, roughly 2/3 or 3/4 of the time, in a way that can't be modeled explicitly, only statistically. On the right are various models that have been put together of the changing obliquity's influence on the amount of water sublimated from the polar cap. Higher obliquity, you get more heating of the polar ice, you get more water. You would get a 10 times increase in the amount of water above 30 degrees obliquity and 100 times or so above the modal value, the peak value in that distribution of 42 degrees. One thing to keep in mind, it does not appear that the increase in water by itself leads to an increase in the oxygen or hydrogen escape rate, and that's because the proximate source of O in the upper atmosphere, which is the source for escaping oxygen, is CO2 rather than water. So it's a complex coupling. At high obliquity with greater water in the atmosphere, you would expect larger amounts of ground ice. The top panel here shows the distribution predicted for the present epoch for the amount of water in the atmosphere. And this is consistent with the measurements of ground ice derived from the neutron spectrometer. The bottom panel shows a map of ground ice. White is ground ice, by the way, of course. The bottom panel shows the amount of ground ice if there was 10 times more atmospheric water vapor, and you get widespread ground ice. This is not even at the modal value of the obliquity. If you go to 100 times the amount of water, you would have global ground ice. With globally or quasi-globally distributed ground ice, it's likely you'd get a lot of surface ice at the same time. One consequence of this is that, again, you would have more water in the near surface environment during the late Hesperian and into the Amazonian. You would expect that to result in larger polar caps. In fact, this is what is seen. The yellow in the panel on the right shows the Dorsa Argentea formation, which is interpreted as the dirt remnant of an older Hesperian era polar cap. The amount of water contained within the Dorsa Argentea is roughly 20 meters global equivalent layer, and that's comparable to the amount lost to space. What this means is that we have at least a plausible explanation of where at least some of the water from the Dorsa Argentea went. That is, it was evaporated into the near surface environment, tootled around between the polar caps and the atmosphere, eventually was lost to space. My last chart, again on the left, is the geographical variation of the exchange of water. A key point that I want to make, the one thing I want you to remember, if this is all you remember from the talk, is that if you're looking at the history of water, you need to consider exchange between all of the different reservoirs. Exchange is rapid, it is thorough, and it's an important range of processes. You have to look at all of the different places where water can reside. When you do that, what I've tried to do in the talk today is put together the different exchange processes and loss processes, and you do get a consistent picture of the history of water. I have three key aspects. One, coming out of the analysis, one is that the loss of water to space was much greater in the past than it is at the present epoch, driven largely by the higher solar extreme ultraviolet in the past, but also due to solar flares and coronal mass ejections. The amount of water lost would be greater than about 10 meters global equivalent layer since about 3 billion years ago. And that compares to only 2 meters if loss occurred over that time at the present rate. Second is the amount of water removed from the Dorsa Argentea formation. That ancient remnant of a polar cap is similar to the amount that has been lost to space. That provides an explanation of where at least some of the water went. And finally, the greater atmospheric water abundance in the past in the surface and near surface environment due to the larger polar cap and due to higher likely obliquities would have resulted in nearly global near surface ice and very plausibly a lot of surface ice at the over much of the time. And I've left it with that tagline of Snowball Mars. Thank you. And I left a minute.
Thank you. We are about a minute ahead of schedule, so my co-chair can walk very slowly to the podium. We will just wait for 40 seconds or so. I wish I had a joke to tell. Ross, do you have a joke? Okay, so the next speaker is my co-chair, Ross Irwin, who's going to tell us about spatially variable paleoclimates on late Hesperian to early Amazonian something. Mars.
Mars, yeah. Good guess. 4 years ago at the Lunar and Planetary Science Conference, we showed that the largest craters that had formed on Mars after the Noachian period had been eroded differently based on their location on the planet. And this was a sign that at the time that these craters were eroded, the climate varied from one region to another on Mars. The present study has three goals. One is to fill in some gaps in that map. The second is to quantify the amount of erosion that has taken place on these post-Noachian craters. And the third is to constrain when the last erosion took place. And I want to acknowledge my co-authors. Deandra Rodriguez was one of the most productive interns we've ever had. She came to us through the Base 11 program last summer. Amanda Rudolph is a postdoc at the Smithsonian. Alex Morgan is a person who can do nearly anything at the Planetary Science Institute. We're looking at the latest stage of landscape evolution on early Mars. There are different types and suites of landforms that formed on Mars at different points in time, from pre-Hellas to the big impact basins in the early to middle Noachian, the landscape evolution with crater degradation, development of escarpments, pediments, and plains, to the development of valley networks and lakes around the Noachian-Hesperian boundary, I think probably early Hesperian, and then the development of alluvial fans, deltas, and lake valleys around the Hesperian-Amazonian boundary. So we're looking at that latest stage of erosion post-valley networks. We have 4 hypotheses to test. These are really null hypotheses. One is that fluvial erosion of post-Noachian craters was the same regardless of when they formed. Second one, similarity regardless of where they formed. The third is that fluvial erosion scaled with crater diameter, that is, more craters experienced more erosion. And 4 is that fluvial erosion, if any, took place immediately after the impact. We focused on the equatorial region here between the yellow lines at plus minus 30 degrees latitude, because if you want to measure the amount of erosion of impact craters, it's helpful to not have to deal with the mid-latitude ice and dust mantles. The red polygons are the continuous ejecta blankets from the earlier study. The yellow stars are the new sites from 75 to 90 kilometers in diameter that we added in. So basically, we took the earlier study, we had to drop the diameter cutoff from 90 to 75 kilometers in order to fill in this map. The craters were initially categorized based on qualitative differences in erosion, from heavy erosion, where you can see alluvial fans and dissection in the MOLA data, to moderate erosion, where you can see some alluvial fan development in the imagery, but not so much in the MOLA data, light dissection of crater walls. And then there are some which is negligible. Negligible erosion doesn't necessarily mean zero. It just means that you have to have erosion of a certain scale in order to be able to do an apples to apples comparison of a younger crater to an older crater. And so there's a cutoff there. And here are the age results. We're going to go from the oldest craters in this set to the youngest ones on the next few slides. And so the take-home message I hope you'll get here is that the heavy erosion in blue, moderate in green, light in yellow, and negligible in white, as you go from older craters to younger craters, there's no pattern. And there's also no pattern in diameter. So you can see there are some big craters and some small craters that are heavily eroded, and the same is true as you go to younger ages. Again, some smaller craters more heavily eroded than bigger craters. So age and diameter are not the cause of these differences in erosion. We do get to a point here at about N1 of 1400 to 1500 where craters are no longer eroded regardless of where they sit. Isol crater was the best stratigraphic marker that we had because it is in heavily eroded region, but it is not heavily eroded itself. Eddy and Ritchie craters were the youngest craters to be eroded. These are all early Amazonian craters, and that suggests that, as others have indicated from studies of alluvial fans, that this last erosion took place in the early Amazonian. This is Isol crater showing an example of the mapping of the continuous ejecta blanket and the population of superimposed primary craters. We've taken out the buried Noachian craters from the set, and we've taken out the secondary craters to give us a primary crater population, which tracks the Hartmann isochrons very nicely. But again, here you'll see an early Amazonian age of isol crater, which is our best stratigraphic indicator there of the age. Alex Morgan did the volume calculations of the erosion of impact craters, starting with elevation values along the watershed boundary, extracting those from CTX or HRSC DEMs, doing a natural neighbor interpolation to produce a rough estimate of the pre-erosion surface, and subtracting the DEM from the pre-erosion surface to yield an eroded depth and eroded volume. So these are all estimates, okay? I mean, there can be some modifications, infilling, et cetera, that might mess with these. There can be locally some places that we didn't have data. For example, Jones Crater, we didn't have data. But that doesn't matter, it turns out, because the differences in the amount of erosion among these craters are order of magnitude differences. You'll see that the green category, the moderately eroded craters, you range from single-digit numbers of cubic kilometers of erosion up to tens, and then for the most heavily eroded craters, starting with Backhausen, tens of cubic kilometers up to hundreds of cubic kilometers of erosion. So these categories of erosion are real, and they are order of magnitude ranges. So there's a huge difference here. And this was the map from the previous study showing a general pattern here, clustering of the heavy erosion, the moderate erosion, and the light erosion in Arabia Terra. This is the current map, which is much more nicely filled in. And you can see the same clustering here. The blue area, this is where Moore and Howard first discovered large alluvial fans. This is where the biggest alluvial fans are. And then we have zones of moderate erosion around Gale Crater and Xanthe. And Arabia seems to be pretty dry through this phase in Mars history. This is a very different pattern of erosion than what you see in the valley networks. Okay, so jumping back from that to the sort of band of valley network erosion, and that suggests that there's something different in the regional climate here between this earlier and later phases of erosion. In a number of cases, we have craters that are superimposed on the big primary crater and that are also themselves degraded. This has shown up too often to be a fluke. And so we believe that these big impact craters, or at least most of them, sat there for a while before they were significantly modified, enough time for additional craters to form on their rims and for those craters to become significantly eroded themselves. And so that's consistent with a phase of erosion in the early Amazonian. Backhausen crater, in a paper on Eberswald in 2015, I showed good examples from the Holden crater region. For results, Eddy and Ritchie, which are both eroded, and isol, constrain the latest fluvial erosion to the early Amazonian. Okay, the error bars on those crater counts are entirely within the early Amazonian. Fluvially eroded volumes vary regionally by 1 to 2 orders of magnitude. This erosion does not scale with crater diameter or age, and some or all of the fluvial erosion took place long after the impacts. Regionally variable fluvial erosion in the early Amazonian would explain all of the results, consistent with prior studies where people have tried to date individual fans, Grant and Wilson, et cetera. And then it's a different spatial distribution than the Noachian to Hesperian valley networks. The Hesperian to Amazonian regional pattern that we see could reflect regionally variable snowfall, winter accumulation, and snowmelt rate. But it's an interesting pattern that we see here. I mean, I think basically what was happening is in this band where we have a lot of erosion, it's far enough south to accumulate a significant winter snowpack, but far enough north to melt it off quickly, and that we're also getting some moisture brought in from the northern lowlands, and with some preferential erosion along these slopes leading up from the northern lowlands. And that leaves me with 10 seconds. So thank you all very much.
Thank you. Our next speaker is Dan Berman.
Pardon my phlegm. Okay, good morning. Where's the... So Becky Williams and I have been exploring how paleolakes on Mars can be indicators of past climates. So paleolakes on Mars in craters typically come in three forms. On the right, we have open source with inlet and outlet valleys, closed source with valley network fed inlets, and closed source with isolated inlets. So I conducted a survey of candidate paleolake craters with the global CTX mosaic, looking for craters with interior valley networks, alluvial fans, where the apex or steps could indicate lake level, and sinuous ridges, typically interpreted as inverted channels, where the transition from the erosional channel to the ridge could indicate lake levels. And this led to an identification of an unnamed crater in Northwest Arabia Terra that had these features, but with key differences that could indicate wet-based glaciation. So features on Mars presently observed as glacier-like forms typically are considered cold-based with no subglacial melting. These include viscous flow features such as low-bay debris aprons, lineated valley fill, concentric crater fill, small low-bay flow features. And we also observe potential moraines. Terminal moraines, for example, are called arcuate ridges on Mars. Landforms indicative of past glaciation that could be considered wet-based on Mars, such as meltwater channels. These are fresh shallow valleys, which have been interpreted as potential meltwater, proglacial lakes, eskers, kettles, and also cames and scouring could be indicators of wet-based glaciation. These are much less well preserved on Mars. So here's the study area in Northwest Arabia Terra in red, between Deuteronolis and Cydonia Mensae. Here is the study area in Themis imagery and again in CTX. So the crater to the right is 48 kilometers in diameter. I propose to name it Kalkaska after the town in Michigan where I went to summer camp. It is 58 kilometers in diameter. That's a typo. And the depression to the left, Sharon Wilson called it Heart Lake. So here is a little animation. Wilson identified these two depressions as potential paleolakes. The crater has no inlet or outlet valleys or rim breaches, but it has incised valleys on the inner and outer walls, as well as the ejecta blanket. You can see troughs on the inner wall, terrace troughs with melt deposits on the floors. Here's a stepped fan, and emerging from beneath several of the fans are sinuous ridges. Here's a large sinuous ridge extending from an eroded fan on the eastern rim of the crater with valley networks feeding it. Here's some more troughs with some channels on them, another one on the southern rim over here. And on the southern wall, we can see these depressions contain potential ice-rich deposits with filled craters, with valleys extending from beneath them to the crater floor. So looking at the, here's some more ice-rich deposits on the western floor. Looking at this depression, the Heart Lake system, it starts in this eroded crater here that's superposed by Kalkaska, goes through this trough and ends in Heart Lake. There's some potential kettles on the floor, which I'll get to. So I created a series of CTX DTMs using the AIM stereo pipeline. I aligned them to the MOLA datum, and then I blended them with the gridded MOLA DEM to create a regional DTM. I also constructed some high-res DTMs as well for a part of the analyses. I did all my analyses in ArcGIS Pro, including the animation I just showed you. So I conducted geomorphic mapping and produced elevation contours. For the mapping, I mapped the shallow valleys in black, sinuous ridges in yellow, and alluvial fans in green. Here's a closer look at the crater mapping. For elevation contours, I used the apex of the northwest fan that I showed you to get the red contour level, which could be a lake level. The orange one is the highest initiation value of ridges, and the blue dashed lines is the lowest ridge elevation level. Excuse me. Notice that these contours are largely consistent with the Heart Lake system as well, which could indicate that the two bodies of water were interconnected at some point, perhaps by a subsurface conduit. So here's a perspective view of the northern wall and floor. You can see the troughs I talked about, which I'll show later, are U-shaped, potential hanging valleys, the meltwater channels, the large fan or delta, potential cames, those little knobs there, as well as the ridges, which could be interpreted as inverted channels or eskers. If you take a closer look at the surface textures in high-rise imagery, on the left you can see the northern crater wall with some valleys. You see this heavily pitted texture. And on the right, you can see the crater floor is also heavily pitted. The whole region is just pitted like this. I mapped 13 fans in the area. 12 of them are within the crater, and one of them is up in Heart Lake, if you can see that. Here's a high-rise DTM of the northwest fan, which has at least 5 steps in it. And on the right, you can see a close view of the high-rise image that shows heavy pitting as well as polygons. And here's a view of the fan in Heart Lake. It is also stepped, it's more eroded. And if you can see, the orange dotted line matches the apex of that fan as well. So a closer look at the glacial troughs. You can see this valley, the meltwater on the floor, the hanging valleys. 2 profiles from the DTM show a largely U-shaped profile. So I liken this to the post-glacial topography of a valley glacier on Mars, where you have the glacial trough that's U-shaped, the meltwater channels, and hanging valleys. I think it's a pretty good analog. If we look at the ridges, you can see on the left the large one on the floor. On the right, you can see ridges going to Heart Lake. They don't transition from eroded valleys directly into ridges, which inverted channels typically do. Superposed by alluvial fans. They're predominantly sharp crested. You can see in this high-rise image. They're also layered. Here's a profile of that ridge. You can see a lot of variation in the elevation along the profile, and that is much larger than the resolution of the DEM. And that suggests perhaps the water went uphill at some point. Valleys, I mapped 576 valleys, the largest of which starts, you can see on the right, along this depression, and in blue on the left goes along into Heart Lake. Here's its elevation profile. Same, these variations in elevation along the profile are larger than the DEM resolution by quite a bit. Here's a close look in high rise. You can see a wider flat floored channel with an inner narrower channel. And here's farther upstream, you can see the flat floor and the inner channel in profile. That's a high rise DTM. So if you look at Heart Lake system, there's a longitudinal profile on the left going from this eroded crater. You can see the rim there, and it's largely convex. And on the right, a transverse profile shows a largely U-shaped as well. So I kind of liken this to the Great Lakes, where an advancing glacier carved a depression, and as it receded to the left, a proglacial lake. If you look at superficial evidence for basal sliding, potential kettles are found on the left on the floor of Heart Lake, on the right on the ejecta blanket of Kalkaska. Here's the floor of the crater as well. You can also see potential scour marks on the valley walls and on the margins of Heart Lake on the right. I did some age dating. The Kalkaska ejecta is mid-Hesperian. Heart Lake is showed a little older, which is impossible because of the way the depression superposes the ejecta blanket there. So perhaps some of those craters
30 seconds.
are actually kettles. So the floor of Kalkaska is early Hesperian to mid-Amazonian, the fan, mid-Amazonian to late Amazonian, and ice-rich deposits the same, mid to late Amazonian. And these ages are consistent with ages for the glaciers in Deuteronomus Mensae. So I'll leave you with this chronology where the glacier advanced and then receded with basal sliding and melting, valleys, kettles, scouring, and perhaps a stagnant glacier remained in the crater and the depression, leaving the rest of the landforms observed and some remnant ice deposits today. Thank you.
Thank you. Our final speaker for this group of 4 talks is Peter Buehler, who's going to be telling us about massive ice-covered overtopped Argyre Paleolake.
Hi, everyone. Thanks for showing up this morning. Good to see you all. I'm excited to share with you some results that are exciting and surprising from what I found looking at an earlier time of Mars, looking at the CO2 cycle when there was a lot more CO2, water, geothermal heat near the Noachian-Hesperian boundary. And the ingredients are we're going to take a late Noachian icy highlands ice sheet, sprinkle a little atmospheric collapse, and that leads to a ton of basal melting. So let's get started. So here's the geologic context. We have the South Pole, this white dot, basically. This purple line is the areal extent of the modeled CO2 ice sheet. I'm going to show you it's a few hundred meters thick. We have our friend, the Dorsa argentea, late Hesperian, or late Noachian, early Hesperian, remnant ice deposits, lots of orange eskers that are indicative of wet-based glaciation. Sinuous valleys that lead into Argyre crater. Argyre crater is about the size of the Mediterranean Sea, pretty big. There's geologic evidence of breach through Ouzboy Vallis into Margarita Forterra, which is one of the most fluvially incised regions on Mars. Perhaps here's Ares Valleys all the way down to Chrysae Planitia. This is the equator, so that's the scale we're talking about here. Here's the model, the schematic model. We have, atmospheric collapse onto this icy highlands water ice sheets. And if you take nothing else away from the talk, collapsing a lot of CO2 onto water ice sheet. CO2 is a very good thermal insulator, traps geothermal heat coming from below. That leads to a lot of melting. In the model, there's some clathrate that can form. That's a lattice structure of water with CO2 ice inside it, also a good thermal insulator. I'll show model results, and then I'll show what happens to the water after it melts. I consider infiltration into the subsurface, which I think is probably minimal based on very relevant modeling from the Earth sciences. Then I consider the formation of ice-covered rivers and lakes, look at sublimation, and probably infiltration here is very minimal too. In the Arctic and Antarctic, the aquifers close up in a matter of days once there's wetting. So here's some model results. This is the first step, calculating how big the CO2 cap is after the atmospheric collapse. This is based on earlier model that I put together with Sylvain. It's an exchange model between CO2 and the regolith, which is Martian soil, the atmosphere, and the cap. I model obliquity of 30 degrees and 600 millibar CO2 atmosphere. That's based on these previous models by Forget et al. And Soto et al. That's sort of the onset of atmospheric collapse roughly 3.6 billion years ago. That's the conditions. And long story short, here's the atmospheric pressure. If you have a 600 millibar atmosphere, once that collapses onto the pole, you get a bonus 400 millibars more or less of CO2 from the regolith that's desorbed. And you get a polar cap that's conveniently about one bar of CO2 in the polar cap. Once the CO2 deposits, I then model the thermal structure of the cap. Each one of these little bars is a vertical profile for a various parameter space that I vary. So it's a 1D thermal model, geothermal heat, strain heat, latent heat, mass balance, class rate, fair bit of bells and whistles. And I consider glacial flow of the CO2. Turns out that's super slow. So the depth of the CO2 is just set by when it basically melts in the column. I look at a variety of the most important parameter space. So there's low shear heating, high shear heating, then the water ice, no class rates, lots of class rates, 40, 50, 60 milliwatts per meter squared of geothermal heat. Nice variety of parameter space. We have the column water ice is in blue, CO2 is in purple, class rates in yellow. Here's a temperature profile. And what these models are showing is when basal melt halts. So this is the final column. The bottom is set at the water ice melting temperature. And so I then take the remnant water ice, whatever is left in the column, I subtract that from the assumed initial thickness, which is about 2 to 4 kilometers based on previous modeling of the late Noachian icy highland sheet. And then from that, I can calculate volumes. So here is the total volume of melt that I calculate. Again, looking over a pretty large parameter space. Here is the total basal melt volume. This red star is just sort of a run-of-the-mill typical model, middle parameter space. And the key takeaway is here is the volume of R gyre. And the melt that can be produced in almost all of parameter space is quite above the volume of R gyre. So there would be potentially more than enough water to melt an R gyre. So this is just looking at various amounts of class rate, various amounts of CO2 collapse. 2 in blue, black is 3, 4 is purple for how many kilometers thick the initial column was. You can also calculate the melt rate. That's consistent with previous estimates from observation. Then what happens to the water downstream? I adopt the model of Moore et al. 1995 for ice-covered lakes. There's water coming in, freezing on the top, sublimation. The most important parameters are albedo, wind speed, and the water coming in. You can just model that. Turns out you can fill R gyre with an ice lid, and then it can overtop. Rivers is the same model, but including turbulent dissipation, which is just equal to the gravitational potential release as the water goes down and hits the ice and knocks kinetically against everything as it goes down. Adding that term means that the ice lid over rivers is more like 10 meters thick. Lakes, it gets up to like a kilometer thick. I took measurements of the valleys leading into R gyre, ran the model, and estimate flow that's sort of 100-ish meters across, 1 meter deep, 1 meter per second velocity. That's what's happening to the water after it leaves out from under the ice sheet. Here is a model of R gyre filling. So this is elevation inside R gyre. This is the breaching elevation. This is time in years, log scale. Light blue is ice forming on top. Dark blue is water filling up the basin. Here is, again, looking at various parameter space. Maximum water flux coming from the South Pole basal melting. Minimum water flux, maximum sublimation over the top of R gyre, minimum sublimation. The takeaway is for most of reasonable parameter space, R gyre can fill and overtop. In the max water case, it takes about 30 to 40,000 years. The ice lid gets to be a few hundred meters thick. For minimum water influx from the South Polar Cap, more like 500,000 years, and that gets to be about a 1 kilometer thick ice lid. If you assume very high wind speeds or very low albedos, you can make it so that R gyre would not overtop with just the water sublimes out too quickly. I consider that not a reasonable parameter space. We can talk more about that. So for the discussion, this atmospheric collapse triggering basal melting, I think can produce model results that are capable of explaining, several previously enigmatic observations. So it can explain the south polar eskers, these orange dots, without needing to invoke greenhouse gas of the right size and the right age. It can possibly explain drainage from the pole to Argyre, which has been proposed on before based on geologic evidence, but there's no model before that could produce enough water to do that. This one can. This has probably ended up being a steady state cycle. So once the water came out from the pole, water would be subliming off Argyre, may have returned to the pole, sort of completing the loop, creating a steady state cycle in a cold atmosphere environment with no need for climate heating whatsoever. Might also have been latitudinally distributed elsewhere to other catchments outside Margarita Forterra and Argyre. Collapse is set by obliquity, would have been 10,000 to 10 million years at a time, depending on what the exact obliquity history was. But once the atmosphere collapsed, melting is set from below, not from above, heat input from below, not from above. There's probably about a 100 million year window where the atmosphere is thin enough that there's collapse, but there's enough CO2, water, and geothermal heat to drive the heating. And I think this theory is a plausible alternative to the paradigm of some sort of late Noachian heating driving fluvial activity around the late Noachian, early Hesperian boundary. And as predicted, we're over time, shameless plug, there's a paper with all the details. I'm happy to talk. Don't elbow your neighbor trying to take a picture of the QR code. Thanks.
Thank you. And I'd like to invite all the speakers from our first session back up to the stage where we're going to have our first panel Q&A. If you do have a question for any of our speakers, please come up to the front and use the microphones, state your name and affiliation, and to whom your question is being addressed.
This is Hannes Bernhard from University of Maryland. This is for the last speaker. So first of all, I appreciate your artwork. That was awesome. How do you weave in the existence of potential esker ridges on the floor of Argyre? You postulate a lake, and that all the volatiles coming from the South Pole remain in there for, liquid with an ice cover, but there would be a lake floor with massive sediment buildup. So how do we end up with eskers on the Argyre floor?
Is this on? I can't. Yes. Okay. Thank you for the question. So modeling that I performed shows that once you shut off water input into Argyre, the whole lake would freeze out in about 1 million years and then sublime away in another 1 million years. So yes, there's geologic evidence of eskers in Argyre. So it's possible that you enter into sort of a diminished time of water input. The column's mostly frozen. You may actually have water input still from the South Pole that could create flow underneath. You could have liquid water in that environment. Or there's some stabilizing feature like a lag deposit that builds up on Argyre that could be heated up, and you've got a pretty thick column of ice that perhaps could lead to eskers. I haven't modeled all that in detail, but that's a great next step.
As a tiny note, there's a sizable fan coming out of Zurius Vallis, emptying out into Argyre, which superposes those eskers. So there has to have been some influx happening after the formation of those.
Yeah, I think that's consistent. Thank you for pointing that out. I think that's consistent with this obliquity-driven cycling. There could have been certainly multiple flows, multiple times that this happened in Mars's history with superposition of previous events.
Britton Logsland, University of Tennessee. I have a question for the second to last speaker. I didn't catch your name, sorry. I was wondering if for the fluvial features that you saw on the outside and the inside of the crater rim, you sort of investigated precipitation origins, and then you have these hanging valleys with the glacial, well, what you call the glacial ledges before you get down into the basin. And I was wondering if you investigated them as fault blocks rather than glacial valleys.
That's a good question. Thank you. Yes, I considered the precipitation model, and it's certainly possible. If you look at the totality of the landforms in the region, I think it lends itself more to a glacial model. But it's certainly possible that the valleys were formed by precipitation. They're found at all elevations. And there's drainage divides, so it's certainly possible. Faults could have formed those terraces initially that were later filled with glacial features.
Thank you.
Just as a reminder to our online participants, if you do have a question, please type it in the Zoom Q&A.
Roger Wientz, Purdue, and this question is probably mostly for Bruce Jakowski. There have been suggestions in the last 7 or 8 years that a lot of significant fraction of Mars' original water is bound up in hydrated minerals. This probably would have happened more in the Noachian, but I'm just curious, Bruce, whether your atmospheric escape estimates are agnostic to that, or whether they actually have any say in the amount of water that might be bound up in hydrated minerals, or the fraction of water that would be that way.
That's a really good question. In our analysis that we presented today, we only went back as far as the beginning of the Amazonian late Hesperian, because we're trying to extrapolate current processes back in time. Once you get back, say, to the beginning of the Hesperian into the Noachian, you're probably looking at a different climate regime where you no longer know what the composition of the atmosphere is or what the atmospheric cycles look like. So it gets really hard to extrapolate. That doesn't keep us from doing it, but you have to take it with a grain of salt. When we look at the all of the different loss processes, you can estimate how much water has been bound up in minerals just from what's exposed and how much water is in each outcropping. You can tally up from things like D to H how much water has likely been lost through time. You can look at all the sources and sinks and come up with a self-consistent inventory of the water. A significant fraction has been bound up in hydrated minerals going back to the Noachian, but you also have a significant fraction that has been lost to space. Some of it has been lost, locked up in the polar caps today. And there's the uncertain amount of how much water might be present as liquid water or free ice within the crust, and whether it exchanges with the atmosphere on any time scale. So you need to look at all of these different components, the ability to exchange, and the time history. How's that for not answering your question?
I would say pretty good. Thanks.
Caleb Fassett, Applied Physics Lab, Johns Hopkins. This is kind of a question that's sort of in between Ross's talk and Bruce's talk, which is Bruce raised the idea that there's this sort of snowball Mars, but I've always sort of thought that the evidence for ice is mostly been sort of those 30 to pole regions. And so I guess the question is there sort of a self-consistent story where you have a wetter atmosphere, more ground ice that's maybe extending a little farther than that 30 south, but still not in that 15 south to 20 north equatorial zone in this sort of late Hesperian, early Amazonian era based on these sort of modified craters?
Do you want to go first? Or sure.
Okay. Good question. The role of obliquity in the distribution of ice is unclear at this time. I think people are just beginning to explore it. one thing to keep in mind is that ground ice would water would diffuse into the subsurface from the atmosphere and condense out. It's probably water ice in the top meters, not tens to hundreds of meters. And it's unclear what the geomorphological effect of that water ice would be and how long it would last once the ice is removed. That is, I expect that we're not talking about looking at features that are tens or hundreds of meters across, and things at the scale of decimeters to meters might easily be eroded away relatively quickly. So I don't think you can say anything about whether there has been ice globally distributed from the morphology, at least not ice coming in from the atmosphere.
I think based on the impact craters that we've studied, which are more than 75 kilometers in diameter in the equatorial zone and more than 90 kilometers in diameter in the mid latitudes, there is a difference in the predominant style of erosion, the predominant morphology that you're seeing, and that as you get poleward of 30, you get into areas that have accumulated ice over time. In other words, you're sort of snowing on it, and you're not melting that off completely every year. So you're stacking it up, and you're getting into glacial flow, and you're getting into meltwater. As you get poleward of about 45, you're still seeing the ice flow features, but you're not seeing the meltwater features. And then as you get poleward of 60, well, then you're starting to get sort of very, very thickly mantled things. But that spatial pattern, I think, represents a moment in time. And if you were to look at Mars at other points in time, you might very well see a different kind of pattern. But I think the reason why we're seeing the large alluvial fans, the largest alluvial fans really concentrated in that band, is consistent with a winter snowpack accumulating there during a time of relatively high obliquity, but it melting off fairly quickly. And that kind of sort of seasonally sort of melting off fairly quickly. We're not seeing evidence of glaciation there. We also, I don't think, have seen any evidence of periglacial modification of stratigraphy at landing sites. And our landing sites have been really selective, low elevation near the equator. These would have been some of the warmest areas on Mars. But I haven't seen, anything like sand wedge polygons, for example, in the stratigraphy. And that makes me think that at the time when those areas were wet, I don't think they were that cold.
My name is Kate Hendrickson from Rutgers University. I have a question from Ross, so I can't really see from this angle, and the podium's not very well. Hi, Ross. So for these different styles of hydrous erosion that you've been talking about at different periods, do you think that has a significantly different effect on the types of compositional storage of this water into hydrous minerals? Because I'm interested in mineral chemistry. And so are those different types of processes going to have a different effect on the minerals in that region?
Yeah, I think most likely. When you're looking at the Noachian period, obviously there's been a lot of denudation of that landscape. There are basically no Noachian craters less than about 4 to 8 kilometers diameter preserved. So nearly the entire secondary population from the Noachian period is wiped out. The vast majority of the craters that formed on Mars from that time have been wiped out. The large craters have been eroded such that walls have retreated, the floors have filled in, and that kind of thing. But this resurfacing has taken place everywhere. It's global. The valley networks are widespread, but as you can see in the mapping, there's clearly a band of them where they're concentrated. Alluvial fans, I think, as Wilson and Morgan and others have shown, also have quite a large distribution, but the biggest ones exist in a band, and a lot of the others are also sort of concentrated. So it's, I suspect that the vast majority of the weathering that we see on Mars probably dates to the Noachian and that we have some amount of reworking of that, that smectite, shrink swell clay, which on the one hand is, an abundant product of basalt weathering, but also is great at sealing surfaces. I mean, I suspect that's probably how we're getting runoff at the Milwaukee-Hesperian boundary, is you're taking all this smectite clay and you're filling in the holes in the impact ejecta such that you can generate runoff from these surfaces without raining like gangbusters on it.
Mhm.
But those surfaces have all been broken up and so on since that time. So, the valley networks, that's a, kind of its own thing. And then a lot of what we're seeing here, I think, is maybe less chemical weathering during the early Amazonian and more kind of localized physical weathering. At that point, you're transporting gravel, as opposed to weathering stuff down to the sort of silt clay range and transporting it. These are really gross generalizations. I mean, obviously, you're going to have a range of things happening at every point in history, but I think that's the overall pattern is from global degradation of one style to erosion of valley networks, which requires a degree of humidity that we wouldn't see otherwise. And then, this type of thing, I think, is probably best explained by a snow melt.
So, sorry, a little bit of a follow-up on that then. So on these different periods, that means that the composition of our aqueous or similar close to aqueous solutions is going to vary based on the different processes that it's gone through.
I'm going to, at the risk of sort of getting outside my
Okay.
own
That's okay.
range a little bit here. I mean, I suspect that a lot of the concentration of chemical weathering products that you see, the sulfates and whatnot is, that this stuff is precipitating out of the atmosphere into the global soil and is getting brought into the groundwater and then transported. And so we're seeing, I think we're seeing a lot of sulfates in areas where it's been, transported as in the groundwater and then cementing sort of medium to fine grain deposits. And that's also true of the hematite and that sort of thing. So I mean, it's that there is global sediment transport, but then there's also the the groundwater component, which is doing different things.
Thank you.
Hi, Jenny Gulick, University of Arizona and SETI Institute. I have a comment and then a question. The comment should motivate the question. First of all, you mentioned that that your glacier forms from atmospheric collapse, and then you get geothermal melting. One thing I want to point out is glaciers require an active hydrologic cycle where snow is accumulated on the source area, it ablates in the sink area. So it starts a cycle. And, I get that you have a geothermal system that melts the base, which is great, but that's a losing system. And I could also see maybe a localized climate where the water vapor from the melting ice winds would bring the water vapor to the glacier again. But again, it's a losing system. So what you would expect is a series of terminal recessional moraines like we see on Earth today with the climate change. Are you seeing that?
So I think in this case, you're starting with a huge overabundance of water that is then melting mostly vertically down. So I think there are not a lot of moraines that have been observed. I think that would also depend on your sediment load that's inside of the water ice. So if there's not a lot of sediment, I don't think you would see a lot of sediment deposited behind it. The situation you have with the CO2 on top is pinning the temperature, so it's cold on the surface. And I agree that, as you said, that I think there's water coming back and cycling back to the polar cap, and that water can work its way down through the CO2 and rejoin the water beneath it. So that happens because when you put water on top of the CO2, which is already at its melting point at the bottom, that gives a little bit of thermal insulation. The CO2 will come back up and start to bury the water. And so that will cycle back down and allow for additional water to melt.
Okay.
So I think that's a really good question in terms of what other geomorphic markers we can look at. So I would say I'm confident that the melting is producing melts at rates that are consistent with the eskers that we see. So that's good. But it's true, there's not really very well identified terminal moraines that I'm aware of, maybe.
Yeah, and esker
Sorry, I'm gonna
formed
have to
from
cut you-
sediment in the
Sorry, Ginny.
moving in
I
the
think we're going to
glacier.
need to take another
Okay.
question.
Thank you.
Thanks.
We are running a couple of minutes behind, so we'll take one very quick final question. Go ahead.
Lawrence Tognetti, Labyrinths Incorporated and Universe Today. I am a science writer. I'm not here on the job. I just wanted to let all you know I'm here presenting my own research. My question is for Dr. Bueller. You mentioned at the very end of your talk briefly how the changes in obliquity could influence your models. Can I ask kind of if you can maybe go more in depth on that?
Sure. So as Bruce showed in his plots, Mars's obliquity is chaotic.
Yes.
So it sort of diffuses over 5 million years with a 15-degree sort of obliquity cycle every 100,000 years at higher frequency. So you can't tell what specifically that history was, but you do know that the times of low obliquity and high obliquity have sort of this 100,000-year periodicity, and you could enter into long periods also of low obliquity. So that's what I'm talking about. Statistically, you would expect periods of sort of 10,000 to 10 million years of low obliquity. When that happens and the obliquity drops below about 30 degrees, that's when you would expect all the CO2 to collapse out of the atmosphere. So that's sort of the time scales that we're talking about for each collapse event. My point was that the obliquity is driving entry into that collapse state, but once you're in that collapse state, as long as the obliquity is below 30, it could be going like all the way down to 5 or 10 or whatever. But what's driving the melting is not the insulation variation. It's just this steady state input of geothermal heat in the model.
Okay.
So that was the point I was emphasizing there at the end.
All right. Thank you.
Mm-hmm.
Thank you. And let's thank all our panelists again. I would like to invite our next speaker, Madison Turner, the moderator for this session, to the stage for our next talk.
Yeah, so today I'm going to be talking about syndepositional craters and how they can be used to, track our accumulation rates and timescales of different sedimentary deposits on Mars. I use this graphic specifically because there's 3 examples in here, so I wonder if you guys can see them. But more on that. Oops. More on that. So before getting into that, it's good to get some background, which is basically that we see abundant evidence of liquid surface water preserved in the sedimentary rocks on Mars that have led to these beautiful artist renditions that are fueled by very real observations, like this example of preserved delta front at Aberswald crater. Even without these preserved features, it's generally accepted that you would need some liquid water to support things like lithification of sedimentary rocks. However, there's, it's been hard to reconcile this with models of Mars' early climate, basically due to these larger scale solar system parameters that aren't easily toggled, right? Like the luminosity of the sun. And so there have been various mechanisms to try and, reconcile this. One of these methods includes this idea of warming induced by collisions of hydrogen and CO2 in the atmosphere that would lead to these periodic warm episodes throughout Mars history. And since it was since it was hypothesized in 2014, it's been modeled extensively and produced some really useful figures like this one from Wordsworth et al. 2021, where you can see the expected temperature output through time. This is also great because it gives us concrete predictions for what you would expect in the Martian rock record, namely the number of events or the number of peaks in this figure that rise past that 273 line, and the duration of events, which is around 100,000 years. However, at this time, our estimates of sedimentation on Mars are pretty coarse and are unable to be tested against this model. Basically, we get our age constraints from either relative age dating or crater counting, which gives a very maximum duration of how long your sedimentation would have had to have taken. But the uncertainties on this are often large and can range billions of years. But there is a way to test this with syn depositional craters. As I said before, these are craters that form during the accumulation of the sedimentary mound before being subsequently buried by younger deposits. And these are just some examples where you can see a partially exhumed crater with sediment overlying it. And research has been done on these features in the past. It's mostly been, smaller studies or with a different scientific question. But, for our purposes, basically the added gain that you would get if you have the pre-existing crater chronology constraints by the colored dots, this is just showing two scenarios of what you could expect to gain with syn depositional crater chronology in a case where you have slow sedimentation with a lot of craters on top and fast sedimentation with very few craters on the bottom. So basically, if you can perform a systematic search of these features with stratigraphy, then you should be able to constrain accumulation rates for your different geologic units. And that's basically the goal of the study, right? The first question that we're going after is just basically, can we map these craters and can we refine our understanding of sedimentation? And then the second question is, with these craters placed within stratigraphy, can we provide some geologic context and constraints for the early Mars climate models? Whoops. And so that leads to these objectives that we're going to use to address this question. The first two being pretty straightforward, first to map the features and then use a chronology model to constrain the accumulation rates, and then to use the distribution to compare against this H2CO2 CIA hypothesis. And so we chose Meridiani, Planum, and Gale for our test sites because, for a few reasons. The first just being that they're extensively mapped. There's a pretty consistent chronology for both of them. And then the second being that there's actually documented cases of syn depositional craters at both locations. Excuse me. The top is an example from Meridiani and the bottom is an example from Gale. And then the last little gem here is that there is a potential for Gale to ground truth one of these features with the, curiosities traversed so far. And then the feature in red is the syn depositional crater from the previous slide. So to maintain a systematic approach, we employed this kind of gridded strategy using 1 by 1 degree grids like shown here to identify any candidates that we see. And then after identifying the candidates, it became a game of confirmation. First, that it's a crater, and then second, that it's syn depositional, either by identifying connected overlying strata, indurated fill, or strata that's overlying the ejected deposits. And, for this, elevation data was really a key. So for this larger example, HRC was good enough resolution to resolve the things that we needed. But for this example, you really needed CTX to resolve the topography. And, after having this completed list of confirmed candidates, we then were able to place it within the stratigraphy based on these existing maps. And then after that, the entire data set was put through a chronology pipeline that was adapted from Kite et al. 2017, using this few of these parameters that are shown to the right. And ultimately, the frequency of your craters within each unit corresponds to your accumulation rate. So this is just the spatial distribution of map craters for both locations. It's not to scale, just to show where we're seeing things. And this is the first major result of this study. Basically, this is showing the accumulation rates for the different units based on, or where the different units are marked with different colors. And you'll also notice this kind of stereotypical ramped and then leveled out pattern. And the important thing to look at is the leveled out region. This is higher confidence because it's actually constrained by larger craters, whereas smaller craters are more susceptible to erosion. And that's why the larger craters you're starting to see them converge at a single value as well. It's also interesting because, you also notice that Gale does not have very many large craters, so it's actually pretty poorly constrained by this method. The second thing to note is that this is an upper limit on your accumulation, again, because there's this potential that you could have craters be eroded. Oops. And the way that we were able to get these numbers is basically just by averaging out the median value for these shaded regions. And this corresponds to an 80 million year accumulation timescale for Meridiani Planum, which is an order of magnitude less than our previous constraints from crater counting, which is about 300 million years. So that gives one part of this CIA hypothesis. And then the other piece is the number of events. And our initial estimate was just using the stratigraphic units. But it became clear as our mapping went on that this was definitely an underestimate. 90% of the craters that were mapped were actually within a stratigraphic unit, self-contained, instead of on the boundary between two units, highlighting that there was probably saw some pauses in deposition. And then the second thing too is that in most of these places, pretty much every subunit or unit at Meridiani Planum, you did see subunits within them. So even though we take these 4 units in Meridiani Planum as definites, I think it's probable that it's more like 8 at least. So, okay, the figure's not right. It's not showing up for some reason, but basically we can test these against the model scenario put forth in the CIA hypothesis by varying parameters of temperature and the burstiness of the hydrogen, which affects the number and duration of events. And that basically gives you a whole range of the scenarios that would be allowable by the model. And even though it's not showing up on the screen for some reason, basically where the text is kind of showing you the shape of the curve. And our data plots down there, which is within the range of scenarios allowed by the model, which again, you can't see. But then there's this potential that you could have things moving. Whoops. And then finally, the last thing is just to summarize that we were able to constrain these rates to less or to an order of magnitude sooner or better. And then, basically these results are consistent with the CIA model predictions, especially when accounting for the different atmospheric and temperature scenarios. That's it.
Thank you. I'd like to invite our next speaker, Ruby Fulford, to the stage. Go ahead.
Good morning, everybody. My name's Ruby. I will be discussing my work using modeling to guide a search for March's oldest landforms. My work focuses on Mars's pre-Noachian and early Noachian epochs. We define the pre-Noachian as the time period between the formation of the crustal dichotomy and the Hellas impact. From the late Noachian onward, we have fairly well constrained Martian conditions, though of course there are still a lot of open questions. But as we get back into the early Noachian and the pre-Noachian, conditions are much more poorly constrained because the geologic records from these time periods have been largely destroyed by billions of years of impacts, erosion, volcanism, and various other processes, which leaves the relative levels of geologic activity in the pre-Noachian into the early Noachian as a big question mark. To better understand pre- and early Noachian Mars, we ask the important question, how well can landforms from these ancient epochs be preserved? And if they are preserved at all, what do they look like today? To approach this question, we first identify well-preserved analog landforms for various types of volcanic, tectonic, and fluvial Martian landforms. So we'll identify well-preserved lobate scarps, young shield volcanoes, well-preserved valley networks. We then use a model to simulate pre- and early Noachian bombardment on topography data for these analog landforms. We also simulate some erosion. Ideally, these model results will predict what these types of landforms would look like today if they formed back in the pre- or early Noachian. And we can then use model results to guide a search of Mars's oldest terrain for candidate pre- and early Noachian landforms that resemble our results. I have developed a simple model that simulates key processes that have shaped Mars's landscape over the years, including impact cratering, different types of erosion and sedimentation. The model takes topography data as input and alters that topography based on a user-specified formation age for the feature being investigated. We apply cratering following an established crater production function, size frequency distribution, and morphological relationships from the literature. We also apply a simple numerical approximation of erosional processes until 3.7 billion years, after which we assume that erosion has declined. For this project, we use molar topography for various analog features as model input. These features include shield volcanoes, lobate scarps, rift valleys, and valley networks. We assume that the input topography represents the pristine state for these types of landforms, and then our model shows us what these landforms might look like if they formed at the given formation age. We choose pre-Noachian formation ages of 4.3 and 4.15 billion years, an early Noachian formation age of 4.05 billion years, and a mid-Noachian formation age of 3.95 billion years as something of an upper bound. I show examples of results from a series of model runs on Biblis patera, which is our representative analog for a small Martian shield volcano. These images all show a prediction of what this type of volcano might look like at the given formation ages. And as you might expect, the older the formation age I choose, the less recognizable volcano becomes. I'll now go through model results and candidate search results for different types of features we investigated. I already touched on volcanic results a bit, but to expand on that, when we run the model on volcanic topography, we find that these features are recognizable as volcanic from early Noachian formation stages onward, with significant topography often remaining from the latter parts of the pre-Noachian, though some of the typical shield volcano shape is lost. We find a few dozen candidate ancient shield volcanoes scattered around the southern highlands. These are not definitive identifications, but we do use them to set an upper limit on the pre-Noachian or early Noachian eruption rate of 0.003 cubic kilometers per year if they formed over a period of 100 million years. This is a few orders of magnitude lower than the late Noachian to early Hesperian Tharsis forming eruption rate, which is estimated to be a full cubic kilometer per year. So these results indicate that there was likely not a gradual decline in volcanism that was coupled with declining heat flow, and that there probably was indeed a peak in volcanism when Tharsis was forming. These are a few of the examples of candidate ancient volcanoes I found. We use this rift valley sorry about that, in Tempe Fosse as a representative analog for extensional tectonics. We find that these features are recognizable from the latter part of the Pre-Noachian onward, though they are widened and shallowed by the effects of erosion and sedimentation. We find a decent amount of confident extensional tectonic candidates in Mars's eastern hemisphere, especially around the Hellas impact basin. Here's some examples of such features that I think strongly resemble results for an early Noachian formation age. These features have been previously identified as graben associated with the Hellas impact by other authors, but our results imply that they could have formed as more classic rift valleys and then evolved to their current appearance. Their orientation is likely influenced by Hellas because many of them are parallel to the basin's rim, but it's unclear whether Hellas is actually the source of the extension. But regardless of the source, it seems that rifting and extensional tectonics could have been more common on early Mars than it is today. Our model results imply that compressional tectonics might be less well preserved than their extensional counterparts. We use Ogyges rupes as an analog lobate scarp, and it seems to be recognizable for early Noachian formation stages and onward, with some topography preserved from the pre-Noachian. We find some compressional tectonic candidates scattered throughout the Southern Highlands, though we have less confidence in these than our extensional candidates. So we think that some ancient compression is likely, but the nature and extent is unknown. It seems that fluvial features fare the worst under our model. These features tend to be quite poorly preserved, save for the large trunk channels of valley networks like Ma'aden Vallis and Nergal Vallis, for which I show some example results here. It seems that smaller tributaries leading into these larger channels, as well as shallower, densely dissected dendritic valley networks like Paraná Vallis, will not be preserved from the early or pre-Noachian. To make things more difficult, the remnants of large channels like Ma'aden Vallis, I think, resemble the remnants for extensional tectonics that are produced by our model results, which means the two could be hard to distinguish when we're looking at Mars's surface. We find a small number of low confidence fluvial candidates in the Southern Highlands. This is an example. It has a fluvial shape. There's a lot of cratering around. But due to the poor preservation indicated by our model results, it's hard to place any constraints on ancient fluvial activity so far. These three plots show a quantitative summary of some model results for volcanic, tectonic, and fluvial features. For each analog landform, I calculate a % preservation at each formation age by measuring a certain characteristic of the model output and comparing it to the same characteristic of the original topography. So for example, if I'm running my model on Ogyges rupes, I will measure the length of the scarp that remains after the model run and divide that by the original length of the scarp to find the % preservation. And we average these percents over the 5 runs we do for each landform and age. We see for all types of features, partial preservation often as far back as the pre-Noachian, which is very interesting. But the fact that this is partial preservation, not total, even into the early and mid-Noachian, shows us that the early Mars geologic record is very much incomplete, and we're not seeing the full story when we look at the surface. Preservation definitely seems to be scale dependent. Larger features and higher relief features, as you might expect, are better preserved. And we think that there could be fragments of pre-Noachian features that have possibly been misidentified as early Noachian, because just by nature of being preserved, these fragments have to sort of get quote unquote lucky when it comes to bombardment. So they may appear younger than they really are. And here is a map of the candidate features I was discussing. The bright regions are the areas where I did a full, close, systematic search, though I did scan the entire Southern Highlands for volcanic candidate features. This figure displays the concentration of extensional tectonics.
Will you please go to your concluding remarks?
Oh, okay. So yeah, we expect partial preservation of pre and early Noachian features, and our search for candidate landforms has allowed us to place some constraints on early Mars. As we continue to identify candidates and fine-tune our model, we'll be able to put some stronger constraints on ancient activity. Thank you.
Thank you. I'd like to welcome our next speaker to the stage, David Horath.
Okay, great, thank you. So this work is largely a continuation of previous Martian hydrologic modeling work that was focused on individual craters, Jezero and Gale specifically, and trying to understand the behavior and the kind of hydrology of these craters in the context of the kind of depositional environment we might see. For this work, though, I've actually developed a framework for investigating multi-catchment scale regional crater systems, so we can kind of understand what's happening in individual regions, compare different regions with one another, and understand what happens to some of these craters as maybe climate shifts to drier conditions. For this work, I'm just going to focus on two types, open and closed basin lakes. Open, of course, are those that overtop and spill and possibly flow into closed basins or other open basins. You can form these lake chains. Jezero is an example of this. Closed basins lack this outflow, and they're less degraded, but they may have been co-eval with these open basins. And Gale is a good example there. You also, as in Gale, you see kind of this interior layer deposits, and sometimes that occurs in these closed basins. So to do this, I take a process approach. So I'm applying this hydrologic model, which I'm calling the Mars lock model. You can discuss details of this applications at a Tuesday poster. But it has, all the aspects of a kind of the surface processes, subsurface numerical model, and then climate inputs into the model. And it's fairly flexible. You can turn things off, if you're just interested in a surface system, just interested in a subsurface system. In this case, we're in this kind of early Noachian, late Hesperian, late Noachian, early Hesperian period where we have this valley networks. And so here, I'm going to assume a fully integrated system. Of course, that can be shut off and just to investigate the surface component. But for the results shown here, this is fully integrated with all these components in it. And so the way the climate is input is going to be framed in this aridity index. So we have evaporation potential over precipitation. Here I'm going to focus mostly on an arid climate and semi-arid climate. So just kind of a reference with the continental United States here. And so there are really three things I'm focusing on. First, looking at kind of understanding the differences between these open or similarities between these open and closed basin, the hydrology of these open and closed basins, understanding any regional influence. So first I'll focus on a region that's kind of near Jezero crater. I'll call it the Jezero region, and then compare that to a region in Arabia Terra. And then any climatic influence, so going from kind of a wetter to a drier shift. So starting here with some semi-arid results. First, I'll set up the model. We have our region of interest. This is the Jezero region. Jezero is in the bottom right here. We run this model, it has a hydrologic head. There's flow on the surface that produces these lakes. And then what we're really interested in is what's happening at these lakes. So we can get out these different hydrologic fluxes. Here, I'm just going to show maps of these, is the evaporation percentage of the total outflow from these lakes. So there may be subsurface outflow flow through the lakes, overspilling in some of these open basin lakes. And so the brighter, the higher evaporation percentage would suggest that any dissolved solids you're getting into those lakes are going to remain and have the potential to kind of produce this evaporate cemented sediment. And then kind of our lower values are darker diamonds or other shapes are going to be those where we have substantial through flow. Either there's overtopping in the open basin lakes or potentially some sort of through flow in the subsurface, or you're really flushing out any sediment that's making it into these basins. Okay, so we'll stay at this Jezero region. We have a number of open basin lakes and closed basin lakes of interest here. Jezero's the open in the bottom right. And so what we see is a pretty wide range of evaporation percentages from these lakes, both in the closed and the open basin case. Both these lake systems or both these lake types are surface dominated, so it's mostly this surface inflow. And then you're getting a majority of overspill at the open basin lakes, but you do have groundwater through flow at all lakes. So you'll notice these diamonds in the map are actually exoheraic basins. This means that you have through flow through the system. You're not none of that water's remaining. It's flowing through or evaporating out. But so even in the closed case, you're still getting this through flow. And so we can look at a relationship of this evaporation percentage as a function of crater depth. There's some kind of increase in evaporation percentage as you get to deeper craters. This is because either you're kind of perched above, so you have kind of groundwater through flow at the shallower craters, or you're able to fill that kind of open basin and overspill pretty quickly when it's fairly shallow. And then the right plot is just the surface inflow ratio to groundwater inflow, and all of these are above this one line. But the key here is that the closed and open basins are behaving very similarly. So now shifting to another region, we have this region of Arabia Terra with a lot of open and closed basin lakes. What you'll also notice is about 4 interior layer deposit craters on the western edge, and we'll look at those as well. So we see something similar to Jezero. The closed basin lakes are slightly drier, but you generally get these exoheraic basins. There are a number of endorheic, so these are those that any sediment that goes in is going to remain. There's going to be no overspill or through flow. And it's slightly drier than the Jezero region because you have a slightly steeper slope in the Jezero region. And then some of the highest evaporative percentages are in these kind of deep interior layer deposit craters. Okay, so now finally shifting to kind of looking at climate. So we've been looking at these semi-arid cases. Now I'm going to show a semi-arid case on the left, an arid case on the right. So for Arabia Terra, these open basin lakes largely fall out of the model. About almost 50%, completely disappear. You have more of an elevation dependence in this evaporation percentage, and they largely you see a pretty large increase in your evaporation percentage in these cases. Closed basins largely remain, right? They're a little bit less degraded and they're deeper, so you have more of these, sticking around, but the evaporation percentage largely stays the same. They're already fairly dry even in the semi-arid case. Okay, so Jezero, though, you see the majority of open and closed remain. You do have a significant increase in your evaporation fraction for the arid case at Jezero and the open basin lakes here. Closed basin, not as much, kind of like Arabia Terra. But you do see a few of these endorheic basins kind of form for the closed basin in this dry, arid case. Okay, so just to look at our, frame this as the crater depth and evaporation percentage here, we have this kind of increased relationship. So I'm going to flip through to drier conditions, first going to a dry semi-arid and then an arid case. So first, dry semi-arid, not a huge change in this relationship, and some slight increase in your evaporation percentage. But then in this arid case, this outflow the surface outflow particularly completely drops out. You don't see a huge change in these closed basins, but the open basins, a significant increase in this evaporation percentage here as you lose that outflow. And then looking at the groundwater, which may be important for kind of retaining these closed and interior layer deposits. So as we shift to a slightly drier climate, you have a slight shift in your groundwater inflow percentage. So now, these interior layer deposits particularly and the closed basin lakes are now receiving kind of a higher percentage of groundwater. And then that's particularly the case at this arid climate. So these receive kind of the largest percentage of groundwater flow in these models. Okay, and just to conclude, so in the semi-arid case, open closed basins are similar. They're surface driven. You have through flow at all these lakes. There are some regional differences. In this case, just between this Jezero and Arabia Terra. Of course, the goal is to look at other regions as well. And that's largely due to kind of these differences in groundwater outflow that cause a steeper slope in the Jezero region near the the dichotomy boundary, and incidus as well. And so the wet to dry shift will cause a significant loss in open basins at the Arabia Terra region. But these closed and interior layer deposits, not ideals, will remain due to this kind of increase in groundwater flow. So yeah, I mean, come talk at the poster and any applications. It's a flexible model that can look at different states in Mars aqueous history. Thank you.
Thank you. I would like to invite now our final speaker for this set of talks, Morgan Carrington, who's going to be telling us about a tale of the two planets' canyons.
Good morning, everyone. My name is Morgan Carrington. I'm a third-year graduate student at UT Austin. And for my literature fans out there, I'm going to tell you a little bit about the tale of the two planets' canyons and the modeling of amphitheater-headed retreat that we've been doing on Earth and Mars. Okay. So on the left, I have an example of what these look like on Earth in Kohala, Hawaii, and an example of what they look like on the right on Mars in Nergal Vallis. And so amphitheater-headed canyons are morphologically unique in sized valleys with deeply entrenched, stubby curved canyon heads, steep side walls, and they maintain near constant valley width from head wall to outlet. And as these two images show really nicely is how morphologically similar they are on both Earth and Mars. And it's that similarity that's driven the need to better understand the formation processes the processes responsible for their formation, which has led to the proposal of two end-member formation processes, groundwater seepage and overland flow. Looking first at groundwater seepage, this is the driving process behind sapping erosion, where groundwater flow is preferentially directed along the contact between two stratigraphic layers with contrasting permeability to an emergence point within the head wall called the seepage face. And that's shown in the blue box on the right-hand cross-sectional schematic of a canyon head. At this seepage face, there's increased weathering, which leads to weakening and eventual erosion of this basal part of the head wall that undermines and eventually drives propagation of this canyon head upstream. Looking at overland flow, this can kind of be thought of as the more traditional waterfall process, where now the flow is directed over the lip of the canyon, as shown by the orange box, again on the cross-sectional schematic. And here, now the undermining process is being driven by plunge pool erosion due to the accelerated flow over the lip of the canyon, or depending on the substrate and how fractured it is, by block toppling, which is again focused more on the lip of the canyon and the substrate in that area. But what we're really focused on is looking at overland flow as a hydrologic process and understanding and assessing how well a simple model formulated for overland flow, specifically using upstream surface drainage area, can reproduce the observed landscapes. And furthermore, comparing how the results of this on Earth versus Mars. And so we look in two regions on Mars within the larger Tharsis Rise and Valles Marineris, Hebes and Eckes Chasma, which are collapse and outflow channel landforms, which are indicated on the left-hand image by the solid box. And then Ias Chasma, which is the northwestern portion of Valles Marineris, and that's indicated by the dashed box. On Earth, we focus on four main study sites within southeastern Utah, Tarantula Mesa, Hans Flat, White Rim, and Escalante. And each of these four sites have been chosen because they each have a unique expression of two stratigraphic contacts with contrasting permeability. And it's also important to note that Tarantula Mesa has been studied by Ryan and Whipple 2020 and Escalante by Lady and Malin 1985. And so we're interested in building upon the studies that have been done and what's been found in those. And so in each of these regions, which are the study sites, taking Tarantula Mesa, for example, we break them down into systems where all of the canyons within that system share a common outlet. So that's shown here on the bottom right hand by the system outline, which is also the system's watershed. The multicolored lines are the individual canyons, and then the outlet is the magenta dot. And so in each of these regions, systems, and individual canyons, we apply a Nick point retreat model adapted from Crosby and Whipple 2006, where Nick point retreat velocity is related to upstream surface drainage area through a power law relationship. And it's important to note that there are two constants, two model parameters, the efficiency of retreat constant C, which is important to note that it's relative time, and P, the power law dependence on drainage area, which is non-dimensional. And the current results that I'm going to show utilize the same best fit values as developed by Crosby and Whipple 2006. And so looking at what this model looks like in action, you're looking at an example system on Mars and Eckes-Chasma on the left-hand side with the multicolored lines being the individual canyons, and on the right, a GIF of what we're really doing in these region systems and canyons. And so you're looking at the profile lines along each of these individual canyons where we collect upstream drainage area over incremented steps. And what we're really looking at is how well we can simultaneously reproduce all the canyon heads, the modeled canyon heads, to this bright orange star, Hookham, that's about to pop up. That's telling us how, quote unquote, well this model is working. And kind of what we're looking at is the model misfit between the modeled Nick points and the observed head walls. And so getting into some of the results that we've been seeing, starting first with the fact that the channel profiles are distinct between Earth and Mars. So the plots that we're looking at are distance from the outlet on the x-axis and on the y, elevation. And the first thing that we're seeing is that Martian canyons tend to be an order of magnitude larger in depth and in length than they are on Mars, as shown by these brackets here. And another thing we've been seeing with the channel profiles is that on Earth, upstream and downstream of the canyon heads, we see that they're normally graded channel profiles, meaning that they're concave up, which is something that we see in other incised valleys on Earth. Contrasting that, on Mars in Eckes-Chasma, we are seeing that, and I guess all the chasmas that we've been looking at, we've been seeing that downstream of the head wall, the channel profiles are more linear. And though they are distinct from Earth, that is something that has been observed in other incised Martian canyons or Martian valleys. And upstream of the Nick points, we are observing pretty much flat upstream surfaces. The other thing that we've been seeing is that Martian canyons typically have larger remaining upstream drainage areas. And so the plots that we're looking at are distance from the outlet on the X and fraction of the remaining upstream drainage area on the Y. And so what we're seeing is that on Mars on the left, or on Earth on the left, they're very close to being finished with their upstream drainage outlets. Whereas Mars, there's a range of available upstream drainage areas left. And because our model is so dependent on upstream drainage area, as shown by the formula up at the top, we are seeing this in plots of relative velocity. And so what we're looking at are those relative velocity plots of fraction of model runtime on the x-axis and distance from the outlet on the y. And on the left, what we're seeing is that all the canyon heads are along this slower moving part of the model, which is telling us that they've again mostly reached the end of their available upstream drainage area. Whereas on Mars on the right, there's a bit more of a range. Some are moving slow and some are moving fast. And so we're kind of trying to think about what this means for the implications of the early Mars surface, whether it speaks to the inability of these fluvial valleys to efficiently incise into their substrates based on perhaps maybe limited integration of the upstream surface, or whether this is more in support of the more limited or episodic activity of surface water on early Mars. But what we're really interested in focusing on is, again, how close we can simultaneously reproduce all these canyon heads within the system. And that's this normalized, minimized model misfit that is shown by the dashed line on these plots. And so on the left, we see it's about 0.02, speaking to 2%. The model Nick points are within 2% the observed head walls. And on right, on Mars, we see it's about 10%, which is pretty good, but maybe not as good as the Earth model result. And so that is something that we've been seeing in all of our results, and that on Earth, on average, we can reproduce the observed canyon heads within 7% the distance of the observed head walls, whereas on Mars, it's about 20%. And so it's not doing too bad on Mars, but it is maybe not doing as well compared to Earth. And we see that there's a larger range in the results that we're getting. Some are doing really well and others are not. But in summary, the Nick Point model is working pretty well on Mars, but it is in fact working better on Earth. And so something that we're trying to think about is, again, what the implications are of the large remaining upstream drainage areas and what that may mean for the early Martian climate, or the key fluvial erosion characteristics of Mars's surface, as well as working through CMP parameters. But preliminary results are showing that C has no effect on our model misfit results, which is telling us that this relative time approach is pretty appropriate for the use of this model. But with that, I thank you.
Thank you. And please could all of our speakers from this block return or remain on the stage. And we will now have our second Q&A session. If you do have a question for any of the speakers, please come up to the microphones at the front and state your name and affiliation. If you have a question and you are online, please type it into the Zoom Q&A.
Hi, Reed Parsons, Fitchburg State University. My question is for Morgan, the last speaker.
Yeah.
I really enjoyed the talk. I had a question about the scale difference between Mars and Earth and how that spatial scale may have an influence on your results. Specifically, I noticed you didn't use the Kohala region that you showed in the introductory part of your talk as something that might be more scale relevant to Mars. Was there a reason you didn't include the Kohala data?
Is this on? Yes, it is on. I can hear myself. I don't think we weren't necessarily thinking more about the scaling thing, although that is a really good point and something to consider. We were more so considering the lithologic controls and something that maybe hasn't been done as much, and trying to see what those results may look like in relative to Mars. And so that was kind of the driving decision behind that. But that is a really great point.
The lithology might be fairly similar, though, with Hawaii basaltic compositions similar to what you might be seeing in Mars, too. Just an idea.
Okay, thank you.
Hey, Joel Hurwitz, Stony Brook University. I had a question for the first speaker. Is it Madison? Yeah, hey, I just wanted to make sure I understood that for the accumulation of the Meridiani platinum deposits, it was 800,000 years of sort of warm episodes within an overall 80 million year sort of total accumulation time. Did I understand the accumulation times correctly?
Okay, on. Yeah, so that's a good question. Basically, so it is, I guess, the minimum time that you could get would be 800,000 years, because you have these 8 stratigraphic intervals, and each of those from the hydrogen the CIA model would be around 100,000 years. So if it's like all that warming, then that would be your time scale. The time scale that we got was for the whole stack based on the thicknesses of the whole thing. So it includes hiatuses and deposition. So it includes the unconformity length scales. Does that make sense?
Yeah, it does. I was sort of thinking back to an old paper that I wrote with a few people in 2010, and the accumulation times there are pretty short, and actually short enough if it's 800,000 years that it might you might be in a situation there where you're sort of burying so much oxygen in the deposit by oxidizing it that Mars can't get rid of the sort of complementary hydrogen reservoir fast enough. So it sort of has the effect of net reducing the atmosphere, which might serve as a positive feedback on like the CIA, but it might be sort of an interesting thing to look into.
Yeah,
cool.
Yeah, definitely. Thanks for your question.
Yep.
Hi, Britton Logsdon, University of Tennessee. I have a question for Dave. I was curious if you had modeled changes in groundwater influx without associated changes in aridity. I was sort of inspired by what Ross had said about smectite mantling the surface and preventing infiltration, and not necessarily changes in precipitation.
Right, right. Yeah, those have been run on like the individual Gale and Jezero to look at, how changes in kind of assumed recharge are going to, affect how much groundwater you get. So yeah, those have been run. I mean, yeah, you reduce, you get less groundwater flow in. Yeah, you drop your water table, you lose a lot of the perched lakes and things, but it's definitely something, that it will go into kind of this work as well, I think. So
Awesome. Thank you.
thank you.
Hello, James Haber, Smithsonian. I have a question again for our last speaker. You talked a little bit about lithology and permeability and how that affects the groundwater and stuff like that in these head canyon formations. How does that aspect come into sort of the differences in fit for your model versus terrestrial versus Mars, and any other different field sites that may fit Mars a little better or something like that?
This is a very convoluted question, and I'm going to do my best we can talk a little more later, but I'm going to do my best to consolidate this. This is, I think, maybe for the terms of like layered stratigraphy and like what that may mean for Mars, and like the sites that we're looking at is kind of, again, the driving force behind why we chose these sites. And so trying to get different expressions of that strong over weak stratigraphy, which kind of speaks to the permeability contrast of it all, is the goal. And we have been doing some field work and another project focusing on kind of the canyon heads of it all. But I don't think there's a bad decision on where to run these things. There may be more appropriate, such as the Kohala region, for example. But yeah, I don't know. Can you ask the question again?
No, that's just wondering, what the permeability effects are and how that plays into the model. And
we're trying to parse
very
it all
complicated, I'm
out.
sure.
It's kind of convoluted right now. This is like really, really fresh and just finished. And so we're trying to parse all that out of like our current results. And so hopefully we'll have more updated and a more complete look at it, but we're parsing through it at the moment.
Gotcha. Cool stuff. Thank you.
Hi, Tim Gouge, UT Austin. I have a question for Ruby. Yeah, the mic setup is funky now that I'm blocked. I can't see you. In your model, I'm wondering if it's mass balanced. When you showed the snapshots, it looked like there was a lot of just sort of net lowering of relief. So is there a mass balance you consider, or is there sort of like, should we think about this as like net sediment export from these regions?
We don't consider a mass balance as of now. We were more focused on the impact cratering aspect of the model and the overall like change, I guess, to the original appearance of the landform. So it's good to hear the feedback that it seems like there's just a net loss, because I think that's something I should consider to make sure I'm not creating an artificial loss of sediment. Thanks for your question.
Thanks.
Hi, Eleanor Moreland, Rice University. Question for Dr. Horvath. I'm going to switch mics. I just had a question on the time scale of your hydrologic models. I might have missed it, but do you set a time scale, or what is the type of time scale where you have water in the system?
Yeah, I mean, these are individual. I mean, these are steady state seasonal, right? It's not an assumed, I mean, it doesn't assume how long this will necessarily last, right? And so, I mean, that's something, to check, to look at transient. And I know there's another hydrologic model that is starting to do that as well. And that has been done a little bit in the past, but for these individual catchments and regional models, it's really a steady state, just annual seasonal cycle.
Thank you.
Hi, Ginny Gulick, University of Arizona City Institute. Comment for the person on the left from UT Austin. I had studied the Hawaiian Islands myself and looked at the sapping issue. A couple things I want to just highlight is that the Kohala ones that you're looking at is under a humid environment. So valley development by sapping can really get enhanced. If you look on the leeward side, it's the same composition. You do not see any sapping. That's because that's a semi-arid environment, just like the ones in Utah. So something to keep in mind. It's a very interesting site.
Yeah, absolutely. And you were saying, you said leeward versus You referring to something or?
Yes, Kohala on well, that's a volcano on
Yeah.
Hawaii. So the windward side, it experiences, it's very humid from the trade winds coming from the northeast. On the leeward side, the other side of that volcano, it's a semi-humid environment. So you get a much less rain. It's the same lithology. It's an excellent area to study the effects of climate.
Okay, cool. Thank you so much.
Yeah, you're welcome.
I had a question for Ruby. You talked you showed some of your model results of extensional features around Hellas, and you said I think that they were associated with the impact, the Hellas impact initially, and then they've been later modified by other processes. Was that your working assumption?
We didn't necessarily assume that they formed as a result of the impact. That's something that we think is somewhat unclear. I think some previous investigations have concluded that they're associated with the impact. And we think that their orientation is definitely influenced by the basin, seeing as a lot of them are parallel to the rim. But I don't know that I can conclude that Hellas is actually the source of extension. But either way, we think that they formed fairly early on. Obviously, they have to be after the Hellas impact, but we conclude that they formed very early in the early Noachian and then probably later evolved to their current state.
Jeff Andrews, Hanna, University of Arizona. Question for this first speaker, Madison. Really nice work and a really important topic you're addressing there. A question I have is that crater ejecta can armor sedimentary deposits. We see that with these pedestal craters where sediments have been eroded away. Could that cause them to be preferentially preserved, kind of outcropping from these sediments? And could that bias the results one way or the other?
That's a good question. For the most part, most of the craters that we saw weren't so the one in the method section was underneath an ejecta blanket, or had been kind of like the ejecta blanket was there, and then there was kind of this step of sedimentary rock. So I do think that there's a possibility that we're seeing some of that. However, most of the craters that we looked at weren't under ejecta blankets. But in most cases, even if we are seeing that, it shouldn't matter, because it's like, in the end, it's still like the area, I guess. So yeah, it shouldn't matter for the chronology.
Hello, William Rapin from IRAP CNRS, and thanks for the great presentation. One question for Dave Arthur. On your modeling, you say it's steady state, so the percent of evaporation is what's the outcome of the water? Is supposed to be 100%, and where does the water go in the end?
Oh, well, yeah, I guess.
And yeah, you have groundwater, part goes to groundwater or part go to evaporation, and
Yeah, I mean, I guess it's seasonal, so there are changes, right? I guess you'd say, I guess it's steady state over that season, right? Or brought up to equilibrium. There's no kind of transient climates or anything like that. But yeah, I mean, it's allowed to evaporate and change depth and everything like that. Is that kind of what you're asking? Or?
Yeah, I'm wondering if so you cannot model for no residence time of groundwater, can you?
Well, yeah, it doesn't really have any sort of particle track. I mean, you could maybe get kind of the recharge area, which would give you a sense of flow paths and everything, but groundwater residence time, not so much. Yeah.
Okay.
It's tougher. Yeah.
Okay, we can talk later. Thanks.
Okay.
Okay, and we will wrap up the Q&A here at this point. We need a few minutes to bring ourselves back on time with the next talk starting at 10:25. So if the next speaker is mic'd up and ready to go, we'll proceed. Thank you all very much to the panelists. Okay, and the next speaker will be Gwenelle Caravaca talking about Prow and Company inside the fluvial lenses at Gale.
Yeah, thank you. Good morning, everyone. So today I will get you through what I could say a description of what would have looked like a sunny afternoon in Gale Crater a very long time ago. Or instead, in other words, yes, what are these fluvial lenses that we have found in Gale layered sulfate unit? So first of all, the Gale layered sulfate unit is also known as a mirror formation, and it is the upper part of Gale's stratigraphic column, as you can see here, that we have been exploring with the Curiosity rover since 2022. It is dominated by Aeolian dunes mega ripple, and it is characteristic of what we are seeking, being the global climatic change as the Noachian-Hesperian transition toward a globally aridification sequence. However, within this overall Aeolian settings, we have found several occurrences of meter to decameter scale erosion resistant lenses such as the Pro outcrop and other lenses. And in this presentation, I will talk about 3 of them that I have chosen for the characteristics. The first is a lens that we have been observing on the flanks of the Rafael Navarro mountain. So you can see here an image acquired with ChemCamp's remote micro imager of such lenses. It is quite big. It is about 30 meters wide and up to 2 meters thick, an erosion-resistant lens made of sandstone. But if we can see the conspicuous lens shape at the bottom, what is also interesting to see is that within this lens, we have a lot of amalgamated meter-scale cross-stratification here highlighted in blue. And this is different from the Aeolian setting since these structures are more compatible with a high-energy tractive setting. Another of this example observed remotely was on the flank of South Mountain, so a little bit farther east from the Curiosity traverse. And it is a little bit smaller, only 12 meters wide, but up to 3 meters thick. We are finding again the conspicuous lens shape, but here, what is striking is that it is covered conformably by the Aeolian lighter tone material. So this conformable relationship is very important here to observe, because it means that this darker toned erosion resistant lenses has been deposited contemporaneously with the lighter tone Aeolian dune material. And finally, let's talk about the Pro itself, which is one of my all-time favorites outcrop in Gale Crater. So we have observed this outcrop with the Curiosity rover back in 2022. It is about 18 meters long and up to 1 meter high, and it is an outcrop that is composed dominantly by medium to coarse sandstones with locally layers as low as 6 tons. It is also highly structured, and I will come back a little bit more in detail in the following slides about that. But in a nutshell, the texture and structures here are most compatible with subaqueous deposition. So now again, talking about the sedimentary structures, we have 2 different scales of sedimentary structures. And on this 3D model made from using photogrammetry from the Curiosity rover images, we can see 2 kinds of large-scale structures. The first, highlighted here in red, is amalgamation of 3 to 4 lens-shaped bodies that are about 5 to 6 meters wide. And within these lens-shaped bodies, you can see that we have a lower magnitude of inner cross-stratification with meter-scale cross-stratification here highlighted in blue. So both of these structures at large scale are compatible with a dynamic setting and most compatible with high-energy fluvial channels. So now looking at lower scale structures, we have also 2 families that are distinguished also by their stratigraphic position. On the lower part of the Pro outcrop, we have these centimeter scale, asymmetric and unidirectional ripples. But more importantly, we have here climbing ripples. So these are the best preserved examples of climbing ripples found on Mars to date. And these are very important because on Earth, climbing ripples are very rare, actually, and they are conspicuously associated with very turbulent, overfilled flowing inside riverine channels. So both these centimeter scale structures are also compatible with high energy fluvial channels, just like the larger scale structures. But what is interesting to see is that on the upper part of the outcrop, we have a completely different setting. First, we have symmetric ripples. So I won't say a lot of details about that because Claire, in a few minutes from now, will talk about more symmetric ripples in more detail. But what to know is that it is conspicuously representing very low energy environments. And finally, we have also found what on Earth we are calling the flather bedding. Flather bedding is specific of alternating high and very low energy deposition condition, with high energy represented by coarse-grained asymmetric ripples and recurrent low energy represented by deposition here of very fine-grained cistone material. So this is indicating alternating and recurrent episode of low energy on top of higher energy setting. So as a depositional setting, what does it mean? It means that the Mirador formation as a whole is not only an aeolian setting, but more likely a fluvio-aeolian setting that saw the recurrence of high energy fluvial inputs that would have carved channels in between the aeolian dunes at times where fresh water was flowing. And more importantly, this fresh water was not continuous. It was only recurrent, episodic, and some period of decrease in this water input was characterized, for example, by abandonment of channels leading to formation of some small ponds or even oxbow lakes that were characterized by lower energy setting, leading to the formation of the flather bedding and symmetric ripples at the top of the lenses. But the question that remains is, are these the same sediments between the fluvial and the aeolian settings? And for that, we have looked at the geochemical composition as seen by the ChemCam instrument, and more specifically focusing on the alkali element, and specifically here on the magnesium and potassium content. So on this plot, you can see the content from the fluvial lenses in green and from the regional aeolian bedrock in blue. And we can see a conspicuous difference, especially in the magnesium content, with fluvial lenses systematically being above 5% in magnesium composition. The blue marks here for the bedrock is usually associated with the magnesium sulfate trend, so different from the main composition. But what is very exciting to see is that actually this composition of the fluvial lenses from the Mirador formation quite perfectly plot against another signature that we have found about 150 meters below back in Glen Torridon. Indeed, the fluvial channels of the Glen Torridon area did have this nearly exactly same composition in alkali element. So maybe a relationship between the sources of these fluvial lenses and the former ones that we have seen back in Glen Torridon. But also, now in the minor element, we have seen several anomalies, starting with the lithium, with a lithium content, for example, on this target Ikabaru, which is very, very elevated compared to the regional average, with composition up to 4 times the average in lithium. And this is interesting because on terrestrial realm, we have seen that fluvial leaching was responsible for lithium anomaly. So that is something to dig up in the future. And we also have an associated manganese positive anomaly, but also a specific chromium depletion that has been also observed by EPXS. So what we see from the geochemistry realm is that we have data that are converging with that from EPXS that are in paper submitted by Kat O'Connell and Cooper recently. And this is a specific geochemical signature for the fluvial lenses that is conspicuously distinct from what of the aeolian bedrock. So what to remember of this is that we have seen a recurrence of fluvial lenses as seen by the MSL rover Curiosity within an overall arid aeolian setting. And these very structures, sandstone-based lenses or the evidence of intermittent but recurring fluvial inputs in between an overall more arid sequence. And this fluvial activity has a specific geochemical signature, which is very interesting to track because it has a different source from the overall local material. So these data are arguing for recurrent wet condition and to be taken into account for the different climatic model for the upper part of Gale stratigraphic section. And I will leave you with this view of Gale then and now. Thank you.
Perfect timing. You finished with 1 second left. Joel, you can't beat that, but please try.
I will.
Now I'm very happy to introduce my co-chair, Joel Davis, who will be speaking about in situ characterization of candidate debris flow deposits.
Okay, good morning, everyone. Following on from Gwenelle's talk, I'm going to be presenting on some recent observations that Curiosity also saw, perhaps a distant cousin of the Prow deposits, some candidate debris flow deposits within the Geddes-Valles Ridge sequence in Gale Crater. Before I get started, I want to acknowledge the co-authors listed there, as well as the entire MSL Science and Engineering team for helping us acquire these fantastic sets of data. That is the wrong button. Okay, to provide a bit of orbital context for Curiosity's recent investigation, as Gwenelle was saying, Curiosity has mostly recently been exploring the sulfate-bearing unit, which is generally interpreted as an Aeolian sequence, with the exception of these fluvial lenses like the Prow that we have been seeing. And this is thought to reflect this overall drying sequence within the whole of Aeolus Mons. Curiosity recently exited Geddes-Valles, which is this 9-kilometer long canyon, which you can see very nicely, in the high rise there, and is partially filled by the Geddes-Valles Ridge. So this deposit within the canyon. You can see the rover's current location off to the right of the screen, indicated by the purple star. And Geddes-Valles incisors, as Geddes-Valles incisors the sulfate-bearing unit, we can infer that it is a relatively young feature, potentially recording evidence for late-stage surface water, much younger than the sulfate-bearing unit itself. So just to say a little bit about Curiosity's recent exploration of the Geddes-Valles Canyon, Alex Brick, Bill Dietrich, and others used long-distance observations much lower down the canyon to interpret the Geddes-Valles Ridge deposit as a degraded alluvial fan. More recently, Curiosity has actually crossed over Geddes-Valles Ridge. We did this back in summer 2024. You can see the path of Curiosity shown by the yellow line. And there's a huge amount of data that I really don't have time to go into today. I would encourage you to go and see the 2 posters by Becky Williams, Lucy Thompson, Asta Cowart as well, and others that are going to be in the poster halls on Tuesday and Thursday. But in very brief, some of the key findings: multiple sediment transport sediment transport processes recorded in the Geddes-Valles Ridge deposit, as well as extensive evidence for in situ alteration. Today, I'm going to be talking about 2 specific deposits within the Geddes-Valles Ridge. That is the outcrops called Stubblefield Canyon, and the less excitingly named Linear Ridge outcrops, which were both encountered during the Geddes-Valles Ridge crossing, and how they could be evidence for debris flow deposits. So the first example I want to talk about is one that is known as Stubblefield Canyon. You can see on the bottom right there where these outcrops occur. They're generally found on this 7 to 10 degree sloping surface, the position indicated by the yellow arrows. And the deposits themselves are made up of very angular to sub-rounded, sort of millimeter to centimeter scale fragments, which I think one could reasonably infer could be clasts. You can see a blow up in this M100 image on the left. The best preserved example of this particular, of the Stubblefield Canyon deposits. If they are transported clasts, the transport distance is likely not very far. They've likely been reworked relatively locally, and the deposits are very poorly sorted. We're going to zoom into the yellow box on the next slide. Okay, so this is what one of the Stubblefield outcrops looks like much closer up. You can see that the clasts generally seem to be loosely held together. In some places, you can see this lithotone material binding them, perhaps some kind of cement and or matrix. Some of the clasts do show a greater degree of localized rounding, and if you look to the image on the right, you can see perhaps some hints at stratification within the deposits, but overall there's very little structure. Okay, so how could these things have formed? Well, there were really two sort of broad end-member ideas for the Stubblefield Canyon deposits. One is that we're essentially looking at an in-situ weathering product. If you look at the image on the left, you can see this really, really nice navcam image of this block that is about 2 meters across. I should have put a scale bar in that. But one of the things that you can see in this is that these blocks have this distinct weathered margin, indicated by the yellow arrows. And it's not unreasonable, I think, to assume that perhaps Stubblefield Canyon is just a much more advanced example of this particular process, and that we're looking at an example of in-situ weathering. And if you're interested in finding out more about these deposits, please check out Asta Cowett's poster. The other end member idea is sort of in the right-hand image, that we're essentially looking at sediment transport and deposition. The morphology and topographic setting of Stubblefield are generally similar to debris flow deposits in canyons and on the surfaces of alluvial fans. Or a related idea is that this could be a colluvial deposit. Slope wash that has transported material during freeze-thaw cycles. The idea that I prefer is essentially a combination of the above hypotheses, that we're looking at in-situ weathering to begin with, and then the weathered margins have been locally reworked. Okay, the second set of deposits that I'd like to talk about are these less excitingly named linear ridge outcrops. These are a series of north-south orientated ridges, so downslope. They're situated within the main Geddes Vallis Ridge deposit, so a bit confusing, ridges within a ridge. And they were encountered in sort of the western crossing region of the Geddes Vallis Ridge. The ridges themselves are about tens of kilometers long, a few meters wide, and up to maybe 2 meters high. Their shape is really nicely exemplified by this wonderful navcam image on the bottom there. You can see the white arrows showing the location of these two ridges. And in this particular example, you can see that the ridge forms a parallel pair bounding a trough. And the question that I've really been interested in asking is, are these ridges depositional levees associated with debris flow transport within the overall Geddes Vallis Ridge sequence? This is what one of these things looked like when we were sort of in the middle of the campaign, sitting on top of one of these ridges. You can see that the troughs in between the ridges generally contain finer material, so sand-sized material and much, much smaller clasts, whereas if you look at the ridges themselves, you can see much, much coarser clasts, maybe up to 50 centimeters, a meter or so in size. This is really nicely illustrated in the top right image, which is a HazCam image from Curiosity. However, I should stress that the presence of modern finds, modern sand within this entire sequence really complicates the interpretation. It's likely that it's possible, rather, that this entire sequence has been buried and then later exhumed. So separating primary from secondary is challenging. This is the best image that was probably acquired during the campaign. It's my personal favorite. This really wonderful M100 image. And this is where the yellow box was on the previous slide. It's the best preserved ridge exposure. It suggests that we're looking at a real range of rock fragment sizes, millimeters through to about 50 centimeters in size for this particular example. Loosely packed together, very, very poor sorting and not very much structure overall, strongly consistent with transported clasts. There is a hint at a mud and sand fraction binding the clasts. But unlike Stubblefield Canyon, the clasts themselves are actually texturally similar to the underlying sulfate-bearing unit. So remember, this is what the Geddes Vallis Canyon is incising into. So it's highly likely that this material has been reworked within Geddes Vallis. Okay, so how could these linear ridges have formed? Well, the ridge and trough distribution is similar to debris flow fans on Earth, where debris flow canyons and flows on Earth, where larger clasts are typically pushed towards the flow margins, forming levee and trough structures. You can see a really nice example on the top right there from the Mojave Desert. Debris flows typically produce very, very poorly sorted deposits, including a high fraction of sand and mud. In the rock record, you can see a really nice example on the bottom right. This is from the Permian in Norway, a subaerial debris flow deposit. Of course, I don't think we can really exclude alternatives to this idea. that these are debris flow deposits. The ridges could be banks, perhaps left behind by fluvial channel incision on a debris-covered surface. Glacier moraines as an alternative, or finally, we could just be looking at eroded landslides or rock avalanche deposits. Okay, so in summary, whilst the Geddes Vallis Ridge deposit is highly degraded, has undergone significant deflation and alteration, there are some primary sedimentary textures and structures that remain. We do see some evidence for late-stage debris flow transport within the Geddes Vallis Ridge sequence, so poorly sorted deposits, very large class, candidate levee structures, but I want to stress that this likely acts in combination with other sediment transport processes, as well as in situ ulceration and burial and exhumation. The one final thing I want to emphasize is that we haven't really seen any convincing evidence of sort of purely fluvial transport, so really well-sorted deposits, well-rounded class, or any imbrication within Geddes Vallis. But this really is just the absence of evidence, not necessarily evidence of absence. And with my final 7 seconds, I'll just say thanks very much. Goodbye, Geddes Vallis. You've been fantastic. Thank you.
Outstanding talk, outstanding timing, and very much appreciated. Thank you, Joel. The next speaker, Claire Mondreau, talking about depositional environment and paleoclimate implications.
All right, thanks. Continuing our trend of some aqueous related sedimentary features in Gale Crater, we're looking at the Amapari marker band and the wave ripples that we found there. The Amapari marker band is our local segment of the marker band that has been mapped across Gale Crater. It's mapped by Whites et al. In 2022 and has been investigated by others. In Gale Crater itself, the marker band is expressed as an erosionally resistant sort of bench forming unit that can be observed from orbit. It extends in this map about 14 kilometers across the northwest side of Mount Sharp, but there's also other instances of it in a more patchy exposure around the south and east side of Mount Sharp. So this is a very extensive unit. There were quite a few hypotheses for the formation of it before we actually got up to it. And the rover encountered the marker band in what we're terming Marker Band Valley, which is this valley shown on the right, where the yellow exposure of the marker band is seen around kind of all sides of the valley. We got a lot of different exposures of the outcrop and encountered it up close at the Amapari location on the west side, and then across the southern bench as Curiosity headed back up the rest of Mount Sharp. Oops. So the ripples that we found were very surprising, maybe one of our least expected features. But when we got up to the Amapari location, you can see in the top section or the top image, we have two different pieces of the marker band, and the lower unit is where the ripples are found, and this sort of pattern of erosive or recessive and resistant layers, and the ripple forms are found in the more resistant layers, interbedded by these more recessive layers. They were found across all of the marker band exposures through Marker Band Valley, and then overlain by this other unit of thickly laminated material. And the ripples themselves are very well expressed through these different outcrops. We got some good measurements on the morphology of them at this location and across the rest of it to confirm the type of ripple and the formation environment. Oh, and one other note here. So from the previous one, the marker band unit itself is conformable with the overlying sediment. So it sounds like, or it looks like a continuous sequence of depositional sediment, and then it's not conformable with the underlying sediment, indicating that the marker band was deposited on a surface that already had some topography, and we'll come back to that later. For the ripples themselves, to confirm the expression or the formation of these ripples and the environment, there's three sorts of possibilities for ripples this size: either wave ripples, aeolian or fluvial, and aeolian and fluvial tend to be unidirectional current ripples. Wave ripples have a different morphologic expression. So the marker band ripples at the top row
we looked at a couple different morphologic features to confirm this ripple type. And the wavelength of the marker band ripples, the symmetry index, and the aspect ratio all really conform most closely with wave ripples. The small wavelength of about 5 centimeters is more consistent with wave ripples. Current ripples tend to be 8 centimeters or larger. It's very hard to get very small ripples like these. The symmetry index is the best indicator of symmetric versus asymmetric ripples. Symmetry index of the Amapari ripples is average of about 0.96, so very symmetric. Both aeolian and fluvial ripples would be much more asymmetric. And the aspect ratio as well of these ripples is important for the depositional modeling, but also aeolian ripples tend to have a very, very low aspect ratio. That's the ratio of the height to wavelength. Fluvial ripples can have a wider range, but again, this fits best with the wave ripple environment. And the internal laminations as well, you can see in the top image, the kind of uniformly dipping internal laminations on either side of the crest, which is very indicative of wave ripples as well. So using the morphologic characteristics, we were able to model the formation conditions of these ripples and confirm that they can form in Mars environments. So the orbital ripples, which the aspect ratio confirms for these, scales linearly with wave orbital diameter, so you can get the water depth that these form in. And we used this modeling needs some assumptions about atmospheric conditions. We used both modern Mars and modern Earth atmospheric densities as the two end members. So the wind speeds required for modern Mars are on the top of the x-axis. The wind speeds for modern Earth are on the bottom y-axis or x-axis, and the water depth on the y-axis shows where these ripples form. So the blue zone is where these would form in either wind speed, and you can see that these would be very shallow water, less than 2 meters in just about any conditions. Realistically, the atmospheric conditions were probably in between modern Earth and modern Mars, but the wind speeds required for either are possible. So somewhere within this range of atmospheric conditions, you could have formed these ripples in very shallow, like 2-meter water that was open to the atmosphere, had wind acting upon it during the time of ripple formation. Whoops, I think I skipped. Nope. So this interval of the Amapari marker band is within the Mirador formation, which is very aeolian. Gwinnell mentioned the prow lenses and other lenses which are just below it. And this sequence represents a period of stable surface water within this otherwise aeolian environment. And throughout the lower sedimentary record of Mount Sharp, we have this transition from more lacustrine, more fluvial into more dominantly aeolian. But the prow and similar lenses and the marker band represent intervals within here where we still have surface water. And that's a really important key for kind of the climate evolution, both of Mount Sharp sediments and Mars as well. And so within the marker band, we have about 15 centimeters of the ripples. So we have wind activity acting throughout the deposition of at least 15 centimeters of sediment. We have the lake itself stable with the atmosphere, open to the atmosphere for however long that took to deposit. And we have the evolution of the lake in a greater sense that we can look at from the stratigraphy. So the ripple units at the base of the marker band transition pretty abruptly into this overlying thickly laminated unit. And the transition into this unit and then the evolution of that unit is also consistent with kind of a growing lake environment, a gradually deepening water. So the thickly laminated unit, the laminations thin, gradually going up section from about 1 centimeter thick to about 0.5 centimeter thick. And this is consistent with an environment where you have gradually deepening water and the source of the sediment is getting gradually more distal. And so this is consistent with a growing lake system within this otherwise aeolian environment. This is also supported by the expression of the ripple presence around Marker Band Valley. So we have all of the ripple units were split into 4 distinct sets, which we were able to correlate around Marker Band Valley based on common morphology. You can see from the left to the right is going up sections. So the lower ripple unit in green is the lowest one and then going up from there. And the colored circles represent where the ripples were observed within the marker band, across marker band valley. So the lowest ones are only observed in the western marker band valley. The middle units kind of expand across the rest of marker band valley, and then the continuous and the upper, which are the right two ones and the highest stratigraphically, are the only ones that are observed on the east edge of marker band valley. So this is also consistent with a ripple environment that starts in western marker band valley, where the marker band is actually slightly lower in elevation, and you have a very slight dip rising in elevation towards the east. And so you have the lowest ripple units where the elevation is lowest, and then you have the upper ripple units expanding eastward across marker band valley. And so this is consistent with a rising lake level across the very gently sloped basal unit of the marker band. So if we extend this to the rest of the marker band that Curiosity was not able to investigate, that we can only see from orbit, going across the northwest side of Mount Sharp, the marker band rises in elevation by about 100 meters across this 14 kilometers. So you can see the elevation scale, color scale in the top left, and marker band valley in the little square in the top right corner of that is a local low. And then the marker band through the rest, across the rest of the exposure, is gradually rising with some other smaller variations within that. So if we assume that all of this was a lake environment, that the marker band formed in the same way across the entire thing, this would be a final lake extent of at least 14 kilometers across through this continuous one, and would have been at least 100 meters deep if you look at the difference in elevation from where we see the ripples to the farthest extent of this continuous mapping. So if it was all subaqueous, if it wasn't, we've got other things to figure out as far as how the outcrop expression was consistent across this. With that, I'm out of time, but not out of content. This was a summary of 2 different papers recently published, so if you want more detail, go check those out, and happy to take questions later.
Thank you very much, Claire. Our next speaker is Alex Jones, talking about the Bright Angel Formation in Jezero.
Yeah, hi everyone, my name is Alex Jones. I'm a PhD student over at Imperial College in London, and I'm really excited to take you away from Gale Crater and over to Jezero for the final talk of this session. First, I want to start by asking everyone, I'm sure many in this room are familiar with Jezero, but first I want people to consider what this view might have looked like 3.6 billion years ago. So Jezero is the site of another ancient crater lake. Perseverance has been exploring here for the last 4 years. And there would have been a full lake lapping up against the crater rim there, and there would have been water flowing in through the western inlet channel, Naretva Vallis, which you can see, and feeding sediment into this beautifully preserved western delta deposit, which Perseverance, as you can see, traversed and explored for quite some time before now reaching its current location on the crater rim. But today, I want to take you over to the inlet channel itself, Naretva Vallis, where we see a series of light-toned outcrops exposed across the channel floor. Now, these outcrops comprise the Bright Angel Formation, and that's where Perseverance was exploring between June and August last summer. The Bright Angel Formation was mapped prior to landing by Stack et al. As this Naretva Vallis layered unit, and they hypothesized that this could either be a young channel fill deposit, potentially formed contemporaneously with the fan, or alternatively, this could be a much older unit exposed by incising of Naretva Vallis during its activity. So my talk and my work has kind of been using data acquired by Perseverance primarily by the Mars-Cam-Z instrument, looking at outcrop scale geology, but also supplementing this with SuperCam and Watson close scale observations and some structural information acquired by the RIMFAX team to constrain the relative age of this unit and what the depositional setting of this unit might be. So this is our first view that we acquired properly of the Bright Angel Formation. You can see it's these light-toned outcrops that I've colored in yellow exposed across the floor of the channel. And you can see the margin unit there, this rubbly unit exposed in the wall. This is looking down north into the channel. And we did the majority of our exploration was actually at the location of this red dot, which is where I'm going to show you now. So this is a mosaic acquired from the location of this red dot, and this is an amazing 360-degree panorama, which means we can see both upstream of Naretva Vallis and downstream, so the downstream end points towards the western fan. And you can see this light tone outcrop covers the floor of the channel. And I want to talk briefly about the structure of this unit because it's quite important to its interpretation. So this is a RIMFAX ground-penetrating radargram acquired along the dotted line from the northern contact on the right-hand side of the radargram on Sol 1210 down towards the center of the channel on Sol 1220. And the structure that this radargram revealed, as well as 3D data acquired by the Mastcam-Z instrument and bedding measurements, revealed this synform channel fill-like geometry to this unit, which suggests that it's probably a younger unit that sat in the channel. And these stereo nets are plots from Rob Barnes' work as well, showing this gentle dip to the north in the foreground of this mosaic and rather steep dips into the channel near the northern contact. So first, I want to kind of now walk through some of the stratigraphy that we saw. So looking at the lowest exposed stratigraphy near the northern contact, this is a Mastcam-Z mosaic looking towards that northern contact. And from now on, just for context, I've got some maps as well showing the looking directions of these mosaics and some stratigraphic columns for folks to keep track. And the lowest portion of the stratigraphy, we saw the margin unit there exposed in the wall. We then had this dark lens of material, the Fern Glen Rapids member, exposed just next to that contact. And then we've got these layers of relatively steeply dipping fine-grained light tone rocks of the Chiaba Falls and Halloglades members in the foreground here. And when we abraded the Fern Glen Rapids member, we saw this spectacular texture of these matrix-supported olivine granules. They're supported in this really fine-grained matrix, suggesting relatively rapid deposition. And these olivine granules are subangular to subrounded, and they have very similar compositions to the margin unit exposed in the wall of the channel, potentially suggesting a local source from the channel walls. And we see similar dark tone lenses up section as well. So this upper image is a view looking towards a zoomed out view looking towards that northern contact, shown in the red dashed line. I mean, you can see these dark tone lenses that pinch out a long strike over tens of meters. And the lower image is a view along strike. These are shown by the yellow arrows. And you can see these in some cases planar stratified and potentially have some coarser grained clasts in there as well. But as you can see, the majority of this unit further up section is dominated by these light tone rocks. And these light tone rocks, when we abraded those, they turned out to be really fine grained. So we weren't able to resolve grains using the Watson camera. So that suggests these are mudstones. And actually, even though these are cross-cut by a load of veins in places and nodular textures, where they aren't, we can actually resolve planar laminations, sub-centimeter scale laminations. So we've got these matrix-supported conglomerates forming a minor component of this unit, of this channel fill synform, and the majority of these laminated mudstones. So this is a high-rise DTM view looking down across over to that northern exposure where we saw that stratigraphy. But there was also a set of stratigraphy exposed on the southern channel margin, which I'm going to talk to you about now as well, because we see something slightly different there. So on the left-hand side, you can see the outcrop style that was very similar to what we were seeing on the other side of the channel, these laminated mudstones, really well stratified. But these were truncated and overlain by this pinkish toned outcrop, which didn't seem to have any stratification. And when we looked up close at these, and this unit at the location of the red dot, it kind of looked similar. It looked to be relatively fine-grained, but actually when we looked more closely, hopefully you can kind of make these out. There appear to be these mudstone clasts embedded within this fine-grained material. So I'll highlight a few here. And this is another view showing a similar matrix-supported conglomeratic texture with these mudstone clasts. This is an enhanced color view acquired by the multispectral instrument on Mastcam-Z. And you can also see these dark tone lithic fragments as well. And this central mudstone clast is actually about 12 centimeters big. And there are some that even reach potential boulder sizes, though we're less confident about those. And again, really, really poorly sorted, very similar to some of the debris flow deposits Joel showed earlier. And Alan Trayman has a poster on the composition of some of these clasts, which show they may, particularly the dark tone lithic fragments, may have compositions similar to rocks on the crater rim. And the final bit of stratigraphy that we saw in Neretva Vallis as part of the Bright Angel Formation is this thin sliver of material that I've highlighted with the yellow arrows. That's our Serpentine Rapids member. And this seems to be capping the sequence. And this is a linear embankment that stretches along the southern margin of the channel. This is a Mastcam-Z view looking along strike west. And you can see this sort of topographic high in the foreground here, and this sits on top of the rest of the stratigraphy. And again, uniquely to the rest of the stratigraphy, it appears to be really well stratified, but actually has potential evidence for cross-stratification, suggesting some current reworking of some description. And it also exhibits these conglomeratic textures. So this is a kind of integrated structural lithologic map and cross-section that I've put together, kind of summarizing what I've just spoken about. So as you can see, the northern and the southern channel show these fine-grained laminated mudstones that appear to be filling in the channel with occasional coarse-grained horizons as well. And those are sat on top of those are these really poorly sorted conglomerates with mudstone clasts. And then just atop that is this thin lens of cross-stratified conglomerate. So our working interpretation for these, this seems to be most consistent with a lacustrine depositional setting, where these laminated mudstones formed by suspension settling from standing water, and these coarse-grained horizons that are in there relatively sporadically, maybe debris flow deposits, and potentially these are sourced from the channel walls, given that the class compositions are very similar to the margin unit which comprises the channel walls. And then sat on top of that, we have this really poorly sorted, unstratified conglomerate with classes of material that looks similar to the mudstones of the underlying succession, which may be another larger debris flow coming in maybe through Neretva Vallis or from the crater rim. And then sat on top of that, we have evidence for unidirectional bedload transport, so potentially a shallower water environment. But the unusual thing about these outcrops is they are only present within Neretva Vallis. They're not present anywhere beyond the channel, and they occur at elevations above the maximum lake level implied by the western fan. So this would imply maybe a potential regional lake high stand, but that doesn't seem consistent with the fact that we don't see these outcrops elsewhere. So one possibility is that these represent a valley-confined lake succession. So when we have really steep valleys on Earth, it's very common that those walls will collapse and will have landslides. And these can block the channel temporarily and generate lacustrine conditions upstream only, which might suggest why we've got these light-toned outcrops at Bright Angel and then only extending upstream. And these form very similar sedimentary successions to what we're seeing at Bright Angel. Lots of mudstones, occasional coarse-grained horizons from the channel walls, etc. So this would be a kind of cartoon model for maybe one possible interpretation of these rocks, where maybe originally we have fluvial incision of Neretva Vallis carving out the margin unit. Then we have some sort of downstream blockage, and then we generate localized lacustrine conditions upstream where we have suspension settling to generate that mudstone, laminated mudstone synform with coarse-grained horizons maybe coming in from the oversteepened walls of Neretva Vallis. Then we have potentially a larger debris flow coming in, scouring, a bit like Joel's debris flow deposit, scouring in the underlying stratigraphy, including some of those clasts and reworking them, and depositing that as this large mudstone conglomerate of the Mount Spoonhead member. And then we have a relative maybe regression or an infilling of that lake where we get shallower water conditions where we can deposit those cross-stratified conglomerates that are capping the succession. And then potentially we breach that dam, drain it all away and plane it off to the stratigraphy we're seeing today. And with that, I'll leave it there, but there are a bunch more fantastic Bright Angel talks this week coming up and posters as well. Thank you.
Thank you, Alex. Please don't go anywhere. I'd like to invite the last four speakers back up to the stage for the panel Q&A. Okay, please go ahead, Jim.
Jim Head, Brown University, really a set of excellent talks. Just a comment and a question. The comment is that we have a great terrestrial analog for the rounded conglomerate pebbles, et cetera, that several years ago, colleagues of mine, we studied the post-Reese impact lake deposits as well as sediments coming in from the exterior. And we found a sedimentary conglomerate that in fact we could trace back to the rim of the crater. Okay, definitely, no question about it. We know what the rocks were. They only traveled about 1 kilometer, and yet they were extremely well rounded. And we studied them in detail and the interiors, thin sections, et cetera. And we discovered that they had been impact pre-processed because they were on the rim. They had shock features up the kazoo. That's a technical term for a lot. Okay, and so, you know, they rounded very, very readily and very fast, okay, within 1 kilometer. So be careful about, I know none of you are doing this, but, you know, a lot of these channels come in from outside and look at kilometers and you think, well, maybe they're so rounded they travel for 100 kilometers. Not necessarily the case. So that's a great terrestrial analog, and I encourage you to look at that. There's an ARP 2019 paper in Icarus. Take a look at that. And the question is, what do you know about the provenance of these conglomeratic particles? Are they coming from the crater rim? Is there any evidence that they're actually from the outside, or do we have any data on that?
Is that working? There we go. Yeah, great question, and thanks for the suggestion. In terms of the composition of these, so Alan Trayman has looked a lot at this. We've got a lovely pixel scan So looking at the like really fine scale geochemistry of some of these clasts and some of the features of this conglomerate. And I believe his work has likened some of the lithic fragments to those compositions we've started to see on the crater rim. So that's definitely interesting. In terms of the mudstone class, there's actually some really interesting features, which I didn't have time to talk about, but I definitely suggest you go and see Alan's poster later in the week. There are some really interesting rims to some of the class as well, which suggested they might have formed outside and then have been reworked later, rather than necessarily ripped up from the underlying mudstone. But I believe, you know, the fact that the lower succession also contains a lot of this fine-grained mudstone as well could be a local source as well. Yeah.
Thank you very much. Thanks a lot.
My name is Kate Hendrickson. I'm a PhD student at Rutgers University, and I have a question for the first speaker. So you mentioned chromium depletion in that formation that you were looking at, and I'm really interested in studying kind of ion transport from aqueous alteration, depletion to reinsertion. And on the specifically for chromium, after it's depleted, do we have a broader picture of where it's going and then where that may be redeposited also from that aqueous alteration?
Short answer, no. Longer answer, not yet, because for some being, we were just looking at specific signatures to be able to recognize specific composition, where, for example, when we drive with a rover, we can stop and have a composition of the bedrock. And even if it doesn't look like a fluvial lenses, the geochemistry can say, okay, it is a hidden lens. So that is just for the time being compositional signature of a geochemical facies, actually. But that is a good question. And we want to know where is it coming from or just getting away to. And that is a good question for, I think, later this year, but keeping the note on that. Thank you.
Okay, thank you.
Ralph Lorenz, APL. I also have a question/challenge for Gwenaël. You showed the spectacular terrestrial analog, the Lenschweiss maranhensis on the north coast of Brazil, and they're kind of tropical dunes. And that's sort of evidenced by the green ponds in between them. And there's a very striking biosignature preservation there. When you walk around, you just see this bright dark banding, because when the slip faces avalanche into the lakes, they trap some of that algae and retain a lot of carbon. So that would be something really exciting to see on Mars. But that site is tropical. The river flow is rather uniform. There's not a lot of energy variation in the flow. And you mentioned seeing some textural evidence of turbulent flow. So I wonder, might there be some better terrestrial analogs, maybe in arid environments?
Yeah, that's a good challenge, actually. Thank you, Rebecca, because indeed, Lenschweiss maranhensis are tropical, and also they are. I am using this as a geomorphological analog, because it does look like what Gale would have looked like. But indeed, actually, it's completely different conditions that are leading to that, especially the fact that in Brazil, it's not exactly fluvial channels that are incising in between dunes, but rather rainwater that is ponding in between the dunes. So it looks like, but actually, I'm not expecting the same, for example, astrobiological conditions, because in Gale, we are coarser grained. That's what we are finding in Brazil, in these ponds. And also, since the energy is very higher, especially at the moment that we are incising the channels, I don't think that we will have any good potential signature that could be preserved there. Except on the top of the lenses, actually, where it is that we have the lowest energy condition with the flazer bedding, with the symmetrical ripples. So maybe during that time of ponding, of oxbow laking, maybe there could be sufficiently fine-grained sediment to keep potential elements that would be compatible. But for the time being, we didn't have found this signature, but we have found other signatures that are very interesting. For example, siderite in this bed, and that will be a talk by William Rapin a little bit later this week. So we don't have this kind of signature. But
as a process analog, it has some deficiencies, but as a
Exactly.
rhetorical example, it was beautiful.
yeah, exactly.
Hello, Audrey Putnam, Rice University. I also have a question for Gwinnell. Also interested in the tops of those lenses. You mentioned that those were conformable, and also that there's distinct geochemistry between the fluvial lenses and the aeolian sediment that is around them. And I'm wondering, in order to have that preserved as conformable, does that mean the groundwater table needs to be continuously rising even after the cessation of that lens of fluvial activity? And I'm wondering if the continuing distinction between those two sediment sources gives you constraints on the intermittency and like groundwater table of the system, or sorry, intermittency of the fluvial lenses in the system. Thank you.
So I think it is a two-folded question, and I will answer the first part and then give the mic to Claire, because the groundwater question is her topic. But yeah, I do think that the difference in physical properties of both sediments are helping in having this characteristic signature, that the fluvial lenses are incising, and then maybe there is a fact that maybe impermeability barrier with clay that could help in distinguishing both of them. And then we have the aeolian setting history with groundwater flowing, and I will let Claire answer this.
Sure. So the prow and the marker band together, and also the aeolian sediment that we see in between, is showing this pattern of gradually rising groundwater through this whole section. So not just the prow lenses. Above the prow and the mirador, we get these pinstripe laminations in the aeolian unit, which is usually indicative of very, very shallow groundwater that's restricting dune formation. And so we're seeing from the prow lenses, this kind of intermittent surface breaching of a groundwater table, and then the pinstripe lamination, so a very, very near surface groundwater table, and then immediately above that we get the marker band lake, which is a very expansive surface expression or surface breach of the groundwater table in some way. So all of these together, despite the fact that the mirador is mostly an aeolian succession of stratigraphy, we have this very interesting groundwater story of this gradually rising groundwater table relative to sedimentation. And the preservation of the sediment, the different source of sediment, the marker band also looks like a different sediment source from the surrounding aeolian. And so it's interesting that we're seeing this different sediment source kind of only preserved in the aqueous environments. And I don't know if we have a great answer for that, but it is a recurring pattern that we're seeing.
Thank you.
Hi, Thanos Fidaris from Purdue University here. My question's for Joel Davis. So what is the diversity of clasts in your candidate debris flow deposit? And are there clasts being transported from units like higher in the stratigraphy that the rover hasn't reached yet? Like, are there clasts from the Yardang unit, for example?
That is an excellent question, and one that we've been asking for the last sort of 2 or 3 years, and I don't think we're quite able to fully answer it yet. I think we're pretty certain that we can see sulfate unit clasts. The Geddes Vallis incises into the sulfate unit, so it's likely reworking that material. Whether or not we've actually seen Yardang material is I think that's a bit up in the air. Some people would say yes, some people would say no. We've seen some good candidates. We do think the Yardang forming unit is very, very friable, very, very easy to erode. So we don't really know whether it would have, survived transport down this canyon. Also, the sort of relative emplacement of the Yardang unit relative to when the canyon was actually active, and if there were sort of debris flows transporting material down is a bit unknown as well. But it's also fair to say we've seen a lot of weird stuff as well that we can't really explain. Some material that may have actually formed in place as well, and not just have been transported from higher up Aeolus Mons.
Thank you.
Hey there, David Burt, NASA Goddard. This might be another dual Gwinnell Claire question. You've got me thinking, like that visual of the flazer beds and the climbing ripples basically side by side is locked in my mind, and I'm having a hard time squaring those. Could you extrapolate a bit and kind of talk to what type of process would form that? Like, is there intermittent flooding that you're seeing for this?
Yeah, actually, as you said, it can be mind-blowing to see some of the lowest energy setting being represented just on top or just below the highest possible and highest sedimentary content possible in a channel. But actually, that is something that it is quite common to see on Earth, for example, on beaches. When you have very high ambient flows, sometimes you will be able to preserve, or not preserving the long term, but like hours of days, this kind of alternating very high and very low conditions. So you be able to have climbing ripples forming in small channels with water retreating during the flow, and during ebb and high tide, having this kind of silty drapes being formed. So that is a common analog. But how does it form in the fluvial realm? And that is the second part. Actually, yeah, I think the key here is the recurrent and intermittent way of doing things. That if you are just having a very high flow in sizing and getting a channel set up, and then you will drive water through this channel for maybe hours, days, or weeks, and then you are decreasing or totally abandoning the flow input on that. And you will be just forming a small pond or an oxbow lake, like a small dead meander in between two dunes that didn't ask for anything else. And then by just physically decreasing the energy, you will have this standing body of water that is likely the size of this room, and that will be just subject to wave action, because you have like 50 to 100 centimeter of water is highly sufficient to have a small wave action on that, and then you will be able to record that. But the third part of the question that was hidden is that you also need to have a very quick burying of the sediment, because otherwise they're just lost to erosion.
Thank you.
Britton Watson, University of Tennessee. I have a question for Alex, who's currently hiding behind the podium. I was curious, so you mentioned that Bright Angel is at a higher elevation than any of the recorded elevations that we have for possible lake levels in Jezero. And I was wondering if you'd thought about the very fine-grained nature of Bright Angel and whether or not it would actually have been preserved or even deposited that far, even further out into Jezero crater. I did like your hypothesis with the blocked off channel, but I was wondering if you'd thought about it as potential evidence for a higher lake stand.
Yeah, thanks, Britton. It's a great question and something we thought about quite a lot when we were developing this lacustrine hypothesis. So the real problem I was coming across with reconciling a potential higher lake level. I mean, there are these studies that look at potential terraces around Jezero, which suggest higher lake levels, but we haven't seen Bright Angel-like deposits, for instance, on atop the margin unit, which is exposed in the channel walls, which would suggest that all of that was also covered in water. And presumably a higher lake level at Jezero would predate the deposition of the Western Fan, and you'd have regression there. And any regression there, I imagine all of the erosion would be concentrated in the Retva Vallis rather than, or focused in the Retva Vallis rather than elsewhere, or that's where the focus of the erosion is going to be. Yet we see which would then lead to the greater likelihood that you'd see Bright Angel-like materials everywhere else, but not in the Retva Vallis, whereas we see the opposite. So I think that was what led to the consideration that maybe this could be an isolated lacustrine setting rather than a regional, if that answers your question.
Yeah, no, that answers my question. And it also, I guess, with the assumption that Bright Angel predates the Western Fan.
So the
which we can talk about more later.
Yeah, that because we don't have any clear stratigraphic markers, and Bright Angel is very geochemically unique compared to the Western Fan to link things. But it's something we're working on. We can chat more later.
Yeah, we'll chat later.
Thanks.
Just a couple of minutes left.
Tim Gouge, UT Austin. My question is also for Alex about the mudstone clasts, which are exquisite. Very cool. I think you maybe alluded to this a little bit earlier talking about the rims, but I was wondering if you see any like actual physical deformation of the class that would suggest they were not fully lithified and so more like rip-up class? Or are they fully intact, which suggests a significant amount of time between that mudstone deposition and whatever mass wasting deposited them or ripped them up as scour?
Yeah, it's a great question. So not seen any clearly deformed class suggesting that they weren't already lithified. I mean, generally the mudstone class are a lot more well-rounded than a lot of the lithic fragments, so implying that they were softer, but probably not, you know, literally still wet mud. Yeah, so we haven't seen those.
Quick question for Claire's Joel Hurwitz at Stony Brook. I'm just wondering, does the presence of those oscillatory wave ripples imply like reversing wind currents on a sort of like diurnal basis as an alternative to something like, you know, tidal washing or something like that? Like they are like symmetrical oscillatory shapes, is that right?
Yeah, so they're symmetric like oscillation wave ripples, and you get that if you have wind moving across water and like the wind is unidirectional, but the wave action that results from the wind, so the wave action forms more of a circular current inside the water. So like wave action, the waves that you get moving across the surface of the water underneath the surface doesn't move unidirectionally with it. It actually like rotates. And so the water wavelength determines the orbital diameter of this like rotating current in the within the water column, and then that rotating current within the water column creates this oscillation current on the sediment floor. And so the wind is unidirectional, and then the water movement resulting from the wind is oscillatory on the lake bed, and so you get this oscillation current on the on the lake bed that's forming the symmetric wave ripples, where it's moving the sediment just back and forth over a very small area from like one single wave, basically. And that's creating your little mini oscillation current on the lake bed that's forming the oscillation ripples and moving the sediment back and forth. It's forming this symmetric ripple. And so, yeah, so it's unidirectional wind direction, and the ripple crests actually can tell us the wind direction. So the ripple crests were oriented kind of northwest southeast, and so that's the wind direction's perpendicular. So the wind direction this time would have been about parallel to the crater rim, so kind of like an around the crater interior wind direction, forming these little oscillation currents on the lake floor.
Thank you.
And that's the last word. Thank you very much to our speakers, all of our speakers, and for our panelists who've just joined us here today. Thanks to all of you for joining us. I'd like to give the panelists a round of applause here. The presentations will be online for 30 days if you feel like you've missed some important details, which I'm sure you have. For those of you who have dedicated your lives to studying Mars, for better or worse, richer or poor, etc., I would direct you to the Mazursky lecture, which will be on minerals in the Martian surface this afternoon at 1 o'clock. Speaker is Liz Rampey. That's in Waterway 4, 5, and 6. I guess this room is number 6. And then this afternoon at 2:15 p.m., there's a special session exploring ancient Mars on the Jezero crater rim and beyond, which will pick up on the topics that have been discussed here. And thanks very much, everybody.